Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient dance of continents, the rise and fall of Pangaea, and Earth's patient story written in stone and time. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 400 million years ago, the continents whisper across vast oceans. They drift as fragments, as pieces of a puzzle not yet assembled, each carrying its own cargo of ancient rock and patient time. The planet turns beneath a sky that has only recently learned to hold the proper mix of gases, its atmosphere now thick enough with oxygen to burn methane into water and carbon dioxide, transforming the orange-hazed world of earlier epochs into something that might, from a great distance, appear almost familiar to future eyes that have not yet evolved to see it. Avalonia moves with the slowness of geological dreams, its margins already scarred by earlier collisions. Its basement rocks holding memories of mountain chains that rose and fell before complex life learned to leave its traces in stone. The continent carries with it the fossilized remnants of trilobites and early corals, creatures that lived and died while Avalonia drifted from southern latitudes toward its destiny in the north. Each trilobite eye, with its calcite lenses perfectly preserved in limestone, stares blindly into deep time, having witnessed the shifting of ancient stars across skies no human will ever see. Within these compound eyes lie perhaps 15,000 individual lenses, each one ground and polished by evolutionary processes that required millions of years to perfect, creating optical instruments more sophisticated than anything humans will design until the invention of the telescope. The trilobites that built these eyes crawled across sea floors that existed when the southern hemisphere held vast ice sheets, when Avalonia itself lay near the South Pole and bore glacial deposits that still puzzle geologists who find tropical coral reefs lying directly above Arctic tillites. Baltica spreads its shield of billion-year-old granite beneath shallow seas, its surface dotted with the simple architectures of early life. Stromatolites build their layered domes in the warm waters, each thin lamination marking another day in deep time, another microscopic victory of cyanobacteria over the patient chemistry of stone. The continent's edges show signs of ancient glaciation, evidence of ice sheets that scraped and polished the bedrock during earlier epochs when Baltica wandered near the poles. Here, in formations that will someday underlie Scandinavia, the rocks preserve tillites and glacial striations, scratches in granite that record the passage of ice across landscapes that existed when the atmosphere held no oxygen, when the sky itself was a different color altogether. These scratches run roughly north-south, indicating ice flow patterns that occurred during a period when magnetic north pointed in directions that would seem impossibly wrong to any future compass needle. Only took 4 billion years for these rocks to travel from the planet's first crust-forming events to this moment of quiet approach. Though the journey remains largely invisible, written only in the subtle chemistry of mineral grains and the faint signatures of ancient stress fields, preserved in crystal lattices, Laurentia holds its own position in the dance, its Precambrian heart exposed across what will someday become the Canadian Shield. The continent's western margin already shows the complex geology of earlier accretions, terrains welded together by collisions so ancient that their mountain chains have been worn down to their granitic roots. Within these rocks lie banded iron formations, layered deposits that tell the story of Earth's first great atmospheric change, when primitive organisms began releasing oxygen as waste, poisoning themselves and transforming the planet forever. The bands alternate between rust-red hematite and steel-gray magnetite, each layer representing seasonal or cyclical changes in ocean chemistry that occurred over billions of years, creating deposits so rich in iron that they will someday supply most of the metal for human civilization. Strange that rocks can remember trauma across such spans of time. Their crystal structures holding the stress patterns of impacts that occurred when Earth's day was only 18 hours long and the moon hung twice as large in the sky. Even stranger that the moon's gravitational pull has been gradually slowing the planet's rotation, stealing angular momentum and converting it into orbital energy, causing the moon to spiral slowly outward while Earth's days grow incrementally longer. The spaces between these wandering continents hold their own quiet dramas. Deep ocean basalts form and spread along mid-ocean ridges that will never be mapped. Their patterns of magnetic stripes recording the planet's fitful magnetic field as it reverses and strengthens and fades according to the liquid metal dynamo deep in Earth's core. Pillow lavas accumulate in volcanic chains that rise from the abyssal depths, their rounded forms cooling instantly in the crushing pressure of 3 kilometers of seawater. Each pillow preserves a moment of contact between molten rock and ocean, a sudden quenching that creates glass rims around crystalline cores, freezing the mineral textures that form when basalt cools over the span of minutes rather than millennia. Only took a billion years for the planet to learn how to generate its own magnetic field, though the mechanism remains a mystery that scientists still work to unravel. Their computer models struggling to explain how convection currents in liquid iron can sustain themselves for billions of years without external input. Scientists still debate the exact positions of these wandering lands, the precise angles of their approach toward one another. Paleomagnetic data suggests certain latitudes, but the magnetic record preserves its secrets imperfectly, like a story told through whispers across geological time. Each continent carries its own magnetic signature, its own record of the planet's shifting field. But the story remains incomplete, full of quiet mysteries that no amount of careful measurement can entirely resolve. The rocks hold their evidence in mineral grains no larger than dust particles, tiny compasses that align themselves with ancient magnetic fields, and then locked their orientation into crystal structures that preserve the memory of directions that pointed toward magnetic poles that no longer exist. Magnetite crystals smaller than bacteria contain within their atomic arrangements the memory of field strengths and declination angles. But these microscopic archives suffer from the inevitable effects of reheating, chemical alteration, and mechanical stress, leaving gaps in the record that may never be filled. The ocean between them holds its own patient chemistry, rich with dissolved minerals that will someday become limestone, evaporate beds, and the chemical signatures of ancient seas. Calcium and carbonate ions drift in solution, waiting for organisms that have not yet evolved the ability to build shells, to create the vast carbonate platforms that will characterize later geological periods. The seawater itself carries a chemistry subtly different from modern oceans, with higher concentrations of dissolved silica and different ratios of trace elements, creating conditions that favor the precipitation of minerals that are rare in today's seas. Only took 3.5 billion years for life to learn how to build shells that would survive as fossils in these approaching sediments. Though the first successful shell builders will not appear for another 50 million years, the water itself carries trace elements leached from the continents, strontium and neodymium isotopes that will provide future geologists with chemical fingerprints of these ancient landmasses, signatures written in the atomic structure of seawater that persists even when the continents themselves have drifted thousands of kilometers from their original positions. Somewhere in the depths, volcanic vents create their own local ecosystems, communities of bacteria that thrive in the planet's chemical heat, indifferent to the slow collision playing out above them. These organisms live in perpetual darkness, drawing energy not from sunlight but from the chemical bonds of hydrogen sulfide and methane, creating their own food webs in the crushing depths where no photosynthetic organism can survive. They cluster around the black smokers and white smokers, the mineral chimneys that rise from the seafloor like ancient temples to chemistry itself. Each vent system creating its own microenvironment where temperature, pressure, and chemical composition combine in ways that exist nowhere else on Earth. The chimney walls precipitate minerals directly from the heated seawater, creating deposits of copper, zinc, and rare earth elements that accumulate grain by grain in the abyssal darkness. The water itself moves in currents driven by winds and temperature differences, patterns that will shift and change as the continents draw closer together, as their combined mass begins to alter the planet's circulation systems in ways both subtle and profound. Above the surface, the atmosphere holds roughly 21% oxygen, a concentration that has taken billions of years to achieve and will continue to fluctuate as the planet's living and geological systems find their various equilibria. The sky appears blue for the first time in Earth's history, though no eyes exist yet to observe this transformation from the methane-orange haze of earlier epochs. Only took 4.5 billion years for a planet to accidentally create the exact atmospheric conditions necessary for complex life to flourish on land. Though flourishing remains a concept that lies far in the future, the air itself carries the chemistry of change, with trace gases that will influence climate patterns, chemical reaction rates, and the evolutionary pathways available to organisms that have not yet learned to breathe this particular mixture of elements and compounds. The collision begins not with violence, but with the patience of stone meeting stone across geological time. Avalonia and Baltica approach Laurentia like massive ships in slow motion, their leading edges already beginning to buckle and fold as they encounter the resistance of older continental margins. The process unfolds over tens of millions of years, each year bringing the land masses perhaps a few centimeters closer together, a rate so imperceptible that entire species could evolve and vanish in the time it takes for a single mountain range to rise from the compression. The approach follows curved trajectories determined by the planet's rotation and the complex geometry of mantle convection. Paths that appear random from a human perspective, but follow the inexorable logic of planetary scale forces operating across deep time. Along the approaching margins, the oceanic crust that separates the continents begins to show signs of stress. Deep beneath the waves, the seafloor sediments wrinkle into long ridges and valleys, creating underwater mountain chains that will never see sunlight. The oceanic lithosphere itself, dense with basalt and heavy with the accumulated sediments of millions of years, starts to bend and crack under the pressure of continental approach. Subduction zones form where the ocean floor slides beneath the continental edges, carrying with it the fossilized remains of countless marine organisms that live their entire evolutionary histories on seafloors, destined for burial in the planet's interior. The descending slabs of oceanic crust carry with them entire ecosystems of bottom-dwelling creatures, trilobites and crinoids and primitive fish that become entombed in the sediments and transported into the planet's depths where they will be heated and compressed until their organic carbon transforms into graphite and their calcium carbonate shells recrystallize into marble. The chemistry of subduction transforms the descending oceanic crust into something else entirely. Water trapped within the sediments and volcanic rocks begins to migrate upward as the slab descends, carrying with it dissolved minerals and trace elements that will alter the composition of the overlying mantle. This hydrated rock melts at lower temperatures than dry mantle material, creating magma chambers that rise through the continental crust like slow-moving underground rivers. The process generates volcanic arcs along the continental margins, chains of volcanoes that will eventually weld themselves permanently to the approaching landmasses. These volcanic arcs form their own distinctive ecosystems, with hot springs and fumaroles creating specialized environments where thermophilic bacteria thrive in conditions that would kill most other forms of life. Only took 3 billion years for Earth to develop the recycling system that allows oceanic crust to return to the mantle. Though the mechanism still puzzles planetary scientists who study worlds that lack this convenient arrangement, scientists remain uncertain about the exact timing of these collisions. the precise sequence of events that brought Avalonia, Baltica, and Laurentia together. Radiometric dating of metamorphic rocks suggests multiple phases of collision and suturing, periods of compression separated by episodes of relative quiet. But the margins of error in these ancient dates span millions of years. The record preserved in deformed rocks tells a story of complex interactions, with evidence for oblique collisions, lateral motion, and the rotation of continental blocks as they were squeezed between larger landmasses. Each grain of zircon crystal in these rocks contains uranium atoms that have been steadily decaying into lead for hundreds of millions of years, providing atomic clocks that tick with perfect regularity even as the rocks themselves are folded, heated, and chemically altered by the collision process. The zircon grains themselves are nearly indestructible, surviving multiple cycles of erosion, transport, deposition, and metamorphism while preserving the chemical signatures of the igneous rocks in which they originally crystallized. The approaching continents carry with them their own distinctive fossil assemblages, evidence of life forms that evolved in isolation on widely separated landmasses. Brachiopods and bryozoans that developed on Baltica show subtle differences from their relatives on Laurentia. Variations in shell structure and colonial organization that reflect millions of years of independent evolution. As the continents draw closer together, these separate biotas begin to intermingle, creating mixed fossil assemblages that preserve the moment when previously isolated ecosystems first encountered one another. The fossil record shows evidence of competitive displacement as species from different continents compete for the same ecological niches, with some lineages going extinct while others undergo rapid evolutionary radiation. Strange that life should serve as a geographical positioning system, with the distribution of ancient organisms providing evidence for continental positions that can be determined in no other way. The oceans between the approaching continents grow progressively narrower, transforming from broad expanses comparable to the modern Atlantic into restricted seaways more like the present Mediterranean. This narrowing affects ocean circulation patterns in subtle but far-reaching ways, altering the distribution of nutrients, the formation of upwelling zones, and the chemical composition of seawater itself. Epicontinental seas begin to flood the continental margins as the oceanic basins are compressed and their water is displaced onto land. These shallow seas create ideal conditions for carbonate deposition, with extensive reef systems built by stromatoporoids and tabulate corals that thrive in the warm, clear waters of continental shelves. The reefs themselves become massive carbonate factories, extracting calcium and carbon dioxide from seawater and converting them into limestone formations that will persist for hundreds of millions of years, creating some of the most distinctive and economically important rock formations in the geological record. The magnetic signatures preserved in rocks from this period show evidence of apparent polar wander, the gradual migration of magnetic pole positions relative to the continents. This wandering reflects not the movement of Earth's magnetic poles, but the rotation and translation of the continents themselves as they are shuffled together by the collision process. Paleomagnetic data from Avalonia suggests that the continent rotated clockwise by several tens of degrees during its collision with Laurentia, a motion that can be detected in the systematic change in magnetic declination recorded in successive rock formations. The magnetic field recorded in these rocks reflects the planet's dipolar field geometry, but superimposed on this global pattern are local magnetic anomalies created by iron-rich rock formations, lightning strikes, and even the magnetic fields generated by flowing groundwater. Only took 400 million years for geologists to develop the tools necessary to detect these ancient rotations, though the implications of continental drift remained controversial well into the 20th century. Volcanic activity associated with the approaching collision creates its own distinctive rock formations. Calc-alkaline magmas generated by subduction processes intrude into the continental crust, forming batholiths and smaller plutonic bodies that will eventually be exposed by erosion millions of years in the future. These igneous rocks carry with them the chemical signatures of their source regions, trace element patterns that reveal the composition of the mantle beneath the ancient ocean basins. Volcanic ash layers spread across vast areas, creating time markers that allow geologists to correlate rock formations across hundreds of kilometers and to establish the precise timing of collision-related events. The ash particles themselves preserve tiny glass shards that quench rapidly from the volcanic eruptions, freezing the chemical composition of the magma at the moment of explosion and creating a permanent record of ancient volcanic processes. Individual ash particles may travel thousands of kilometers in the upper atmosphere before settling to Earth, carrying with them chemical fingerprints that allow geologists to identify the specific volcanoes that produce them. Deep beneath the surface, the collision generates metamorphic pressures and temperatures that transform existing rocks into entirely new mineral assemblages. Shales become slates, limestones recrystallize into marbles, and granites develop foliated textures that record the direction and intensity of ancient stress fields. The metamorphic process occurs grain by grain, with individual mineral crystals slowly re-equilibrating to new pressure and temperature conditions, while preserving textural evidence of their pre-collision history. Garnet crystals grow in concentric zones that record changing temperature conditions over time, creating natural archives of the collision process that can be read like tree rings under a microscope. The transformation requires millions of years to complete, with temperature and pressure conditions that would instantly vaporize any living tissue but which allow solid rock to flow like thick honey over geological timescales. The approaching collision affects not only the continents themselves, but also the global climate system. As oceanic circulation patterns change and continental positions shift, the distribution of heat around the planet begins to alter in ways that will influence weather patterns for millions of years to come. The collision process itself releases carbon dioxide through the metamorphism of carbonate rocks, adding greenhouse gases to the atmosphere and contributing to global warming that persists long after the mountain building phase has ended. Only took 500 million years for a planet to develop climate systems complex enough to be influenced by continental geography. Though the feedbacks between tectonics, ocean circulation, and atmospheric composition remain incompletely understood even by modern climate scientists. Mountains rise in silence from the collision between wandering continents, their growth so slow that no single lifetime could witness the transformation of seafloor into summit. The Appalachian Caledonian chain emerges grain by grain from the compression, each crystal of quartz and feldspar finding its new position as continental margins buckle and fold beneath the patient pressure of geological forces. The mountain-building process, known to geologists as orogeny, unfolds according to the physics of solid materials under stress, with rocks that seem permanent and immutable flowing like viscous liquids when subjected to the proper combination of heat, pressure, and time. The rising mountains follow patterns that reflect the geometry of the collision itself. Fold axes align roughly parallel to the continental margin, creating long ridges and valleys that will channel rivers and influence weather patterns for hundreds of millions of years into the future. Anticlines arch upward where the compression is most intense, exposing the oldest rocks in the cores of the folds, while synclines form the intervening valleys where younger sedimentary layers are preserved in downward bending troughs. The folding process occurs on multiple scales simultaneously, from microscopic crenulations visible only under a hand lens to regional structures that extend across entire continents, all following the same fundamental principles of rock deformation under stress. Within the deforming rock masses, mineral grains respond to the changing conditions by recrystallizing into new forms better suited to the metamorphic environment. Muscovite mica develops its characteristic platystructure as aluminum, and potassium atoms rearrange themselves into sheet silicate configurations, creating the sparkle and shine that will characterize schist and gneiss formations millions of years in the future. Quartz grains elongate and develop preferred orientations, creating lineations that record the direction of maximum stretching during the deformation process. The transformation occurs molecule by molecule, with crystal structures adjusting to new pressure and temperature conditions while preserving textural evidence of their sedimentary origins. Only took 4 billion years for a planet to develop the crustal recycling processes that allow sedimentary rocks to transform into metamorphic rocks without completely melting. Though the precise mechanisms of solid-state recrystallization remain subjects of active research, scientists puzzle over the exact height achieved by these ancient mountains. The precise elevations reached during the peak of the orogeny. Thermobarometric studies of metamorphic rocks suggest pressures equivalent to burial depths of 20 to 30 kilometers, implying mountain ranges that may have rivaled the modern Himalayas in their grandeur. However, the relationship between metamorphic pressure and surface elevation remains complex, complicated by the effects of crustal thickening, isostatic adjustment, and the redistribution of mass during the collision process. Paleobotanical evidence from fossil leaves and wood suggests that vegetation zones shifted in elevation as the mountains rose, with temperate forest species gradually replaced by alpine flora at higher elevations. But the fossil record preserves only fragments of these ancient ecosystems. The mountain building process generates its own distinctive rock types, metamorphic formations that exist nowhere else in the geological record. Blue schist metamorphism occurs in subduction zones where oceanic crust descends rapidly enough to maintain low temperatures despite increasing pressure, creating mineral assemblages dominated by blue amphibole and white mica that reflect the unusual pressure-temperature paths followed by the descending rocks. Eclogite forms at even greater depths, where basaltic rocks transform into dense assemblages of garnet and pyroxene that represent some of the highest pressure conditions achieved in continental collision zones. These rocks preserve evidence of burial to depths of 50 kilometers or more, yet they now lie exposed at the surface, evidence of the massive amounts of erosion and exhumation that have occurred since the mountain building episode ended. Granite plutons intrude into the deforming crust as partial melting generates magma chambers deep beneath the rising mountains. These intrusions follow zones of weakness created by the folding and faulting, rising along fracture systems and metamorphic discontinuities until they reach levels where they can crystallize slowly into coarse-grained igneous rocks. The granites carry with them distinctive trace element signatures that reveal the composition of their source regions, chemical fingerprints that allow geologists to determine whether the magmas originated from melted sedimentary rocks, pre-existing igneous rocks, or direct partial melting of the mantle. The cooling process requires millions of years to complete, with different minerals crystallizing at different temperatures and creating the complex textures that characterize plutonic rocks. Strange that molten rock should cool so slowly that individual crystals can grow to centimeter size. Yet, the insulation provided by kilometers of overlying crust allows this patient crystallization to proceed without interruption. Erosion begins almost immediately as the mountains rise, creating a dynamic equilibrium between uplift and denudation that determines the ultimate height and longevity of the mountain chain. Rivers carve valleys through the rising rocks, transporting sediments towards distant ocean basins where they will be deposited as thick sequences of arkose and conglomerate derived from the erosion of granitic and metamorphic source rocks. The erosional process follows fracture patterns created by the deformation, with streams and glaciers exploiting zones of weakness, where joints and faults provide pathways for water infiltration and freeze-thaw weathering. Each fragment of quartz and feldspar that breaks away from the mountain faces carries with it a microscopic record of the pressure and temperature conditions experienced during the metamorphic process, chemical and structural signatures that will persist even after the grain has been transported thousands of kilometers from its source. The rising mountains influence atmospheric circulation patterns in ways that extend far beyond their immediate geographical boundaries. Orographic precipitation occurs as moisture-laden air masses are forced to rise over the mountain barriers, cooling adiabatically and releasing their water content as rain and snow on the windward slopes. This creates rain shadows on the leeward sides of the mountains, establishing climatic patterns that influence the distribution of vegetation. Soil formation. and erosional processes across entire continents. The mountains themselves generate their own local weather systems, with valley breezes and mountain winds creating circulation patterns that exist only in regions of high topographic relief. Deep within the mountain roots, the collision process generates heat through friction and the decay of radioactive elements concentrated in the thickened continental crust. This heat drives metamorphic reactions and partial melting, creating temperature gradients that can be preserved in the mineral assemblages of metamorphic rocks and reconstructed through careful petrological analysis. Geothermal gradients in collision zones may reach values of 30 to 40 degrees Celsius per kilometer of depth, significantly higher than the normal continental gradient of 25 degrees per kilometer, reflecting the enhanced heat production associated with crustal thickening and radioactive decay in granite-rich rocks. The mountain building process creates structural patterns that will influence geological processes for hundreds of millions of years after the collision has ended. Thrust faults carry older rocks over younger ones, creating geological relationships that seem to violate the normal principles of superposition until the effects of deformation are properly understood. Strike-slip faults accommodate lateral motion between continental blocks, creating linear valleys and offset stream channels that record the sense and magnitude of horizontal displacement during the collision. Only took 300 million years for geologists to develop the conceptual framework necessary to understand these complex structural relationships. Though the detailed mechanics of fault motion during continental collision remain subjects of ongoing research and debate. The completed mountain chain stretches across thousands of kilometers, creating a continuous barrier that will influence the evolution of life, climate, and then geological processes on both sides of the collision zone. The mountains rise like a slow geological wave across the landscape, their peaks reaching toward a sky that has witnessed the patient assembly of continents from fragments scattered across ancient oceans. Their roots extending deep into the thickened crust, where the collision continues to reverberate through the solid earth long after the surface motion has ceased. Devonian seas spread between the closing gaps, vast epicontinental waters that flood the margins of the approaching continents as ocean basins compress and their contents spill onto land. These shallow seas stretch across thousands of square kilometers, creating marine environments unlike anything that exists in the modern world, where continental shelves extend hundreds of kilometers inland from what will someday become ocean shores. The water itself carries a chemistry subtly different from modern seawater, with higher concentrations of dissolved silica and different ratios of trace elements that reflect the ongoing weathering of freshly exposed mountain ranges and the volcanic activity associated with continental collision. Within these shallow seas, life undergoes transformations that will reshape the biosphere forever. Armored fish cruise through waters that have never known the presence of sharks, their primitive jaws experimenting with new feeding strategies that will eventually give rise to all vertebrate lineages. Placoderms, some reaching lengths of 10 meters, patrol the deeper channels with crushing jaws capable of breaking through the shells of early mollusks, while smaller forms develop the first true teeth and the neural innovations necessary for complex predatory behavior. The evolution of jaws represents one of the most significant innovations in vertebrate history, transforming filter-feeding creatures into active predators and opening entirely new ecological niches that had previously remained unexploited. Only took 400 million years for evolution to stumble upon the mechanical advantage provided by hinged jaws. Though the transition from gill arches to feeding apparatus required millions of years of gradual modification and countless intermediate forms that left only fragmentary traces in the fossil record. Along the margins of these inland seas, the first forests begin to establish themselves on land that has never before supported complex vegetation. Primitive trees, still lacking true roots and relying instead on rhizoid systems for anchorage and nutrient uptake, create the earliest woodland ecosystems in Earth's history. These early forests consist largely of lycopods and early ferns, plants that reproduce through spores rather than seeds, and require moist conditions for their reproductive cycles to complete successfully. The trees themselves grow in patterns determined by their simple water transport systems, clustering near streams and in areas where groundwater approaches the surface, creating a patchwork landscape of forested wetlands separated by areas of bare rock and primitive soil. The development of soil itself represents a revolutionary transformation of the terrestrial environment. For the first time in Earth's history, complex interactions between plant roots, fungi, bacteria, and weathered rock create layered soil profiles with distinct horizons and chemical gradients. Mycorrhizal associations between plant roots and fungal networks enhance nutrient uptake and create underground communication systems that allow forests to function as integrated ecosystems rather than collections of individual organisms. The soil formation process occurs grain by grain. As root acids dissolve bedrock minerals and organic matter accumulates in surface layers, creating the foundation for all future terrestrial ecosystems. Strange that life should learn to engineer its own substrate, transforming bare rock into the complex chemical environment necessary for plant growth. Yet the process requires millions of years to create soil layers even a few centimeters thick. Scientists remain uncertain about the exact composition of Devonian atmospheres, the precise concentrations of oxygen and carbon dioxide that characterized this period of rapid evolutionary innovation. Paleosol studies suggest atmospheric oxygen levels that fluctuated between 15 and 25%, high enough to support the metabolism of large arthropods, but not so elevated as to make wildfires a constant threat to the early forests. Carbon dioxide concentrations appear to have been significantly higher than modern levels, creating greenhouse conditions that supported tropical vegetation at latitudes that would be temperate or boreal in today's climate. The carbon cycle itself was entering a new phase as terrestrial vegetation began to influence atmospheric composition through photosynthesis and the burial of organic matter in sedimentary deposits. The shallow seas themselves become massive carbonate factories as marine organisms learn to extract calcium and carbon dioxide from seawater and convert them into limestone and dolostone formations. Stromatoporoids build reef systems that extend for hundreds of kilometers along continental margins, creating barriers and lagoons that further diversify marine habitats. These reefs support complex ecosystems of crinoids, brachiopods, and early gastropods, communities that represent the first truly modern marine ecosystems in terms of their ecological complexity and trophic structure. The carbonate deposition process removes carbon dioxide from the atmosphere and seawater, contributing to long-term climate regulation and creating rock formations that will persist for hundreds of millions of years. Coral reefs of this period differ significantly from their modern counterparts, dominated by tabulate and rugose corals that build colonial structures using different skeletal architectures than modern scleractinian corals. These ancient reef builders lack the symbiotic algae that characterize modern tropical corals, instead relying entirely on filter feeding to capture nutrients from the water column. The absence of photosynthetic symbionts allows Devonian reefs to grow in deeper and murkier waters than modern coral reefs, creating carbonate buildups in environments where contemporary corals could not survive. The reef ecosystems themselves support diverse assemblages of crinoids, bryozoans, and primitive fish, creating some of the most biodiverse marine environments in Earth's history. Between the established reef systems and the emerging coastal forests, extensive tidal flats and estuarine environments provide transitional habitats where marine and terrestrial ecosystems begin to interact for the first time. These marginal environments become laboratories for evolutionary innovation, with early amphibians developing the physiological adaptations necessary for life in both aquatic and terrestrial environments. The first tetrapods retain many fish-like characteristics, including lateral line systems for detecting water movement and scales for protection, but gradually develop stronger limbs and more efficient lungs for extended periods out of water. The transition from water to land requires fundamental changes in virtually every organ system, from respiratory and circulatory modifications to new sensory capabilities for detecting airborne sounds and scents. Sediment deposition in these shallow seas creates thick sequences of sandstone, shale, and limestone that preserve detailed records of environmental change and biological evolution. Individual sedimentary layers may represent seasonal or annual cycles of deposition, with winter and summer layers showing different grain sizes, mineral compositions, and fossil content. The sedimentary record reveals evidence of periodic sea level fluctuations driven by glacial cycles, tectonic processes, and possibly astronomical forcing, creating unconformities and sequence boundaries that allow geologists to correlate rock formations across vast geographical areas. Each layer contains its own distinctive fossil assemblage, creating a detailed timeline of evolutionary change that spans millions of years of gradual transformation. The chemistry of seawater during this period reflects the ongoing weathering of the newly formed mountain ranges, with elevated concentrations of dissolved minerals derived from the erosion of metamorphic and igneous rocks. Strontium isotope ratios in marine carbonates suggest enhanced continental weathering rates, while trace element concentrations indicate increased volcanic activity associated with the collision process. The ocean chemistry itself influences the types of organisms that can thrive in marine environments, with some mineral concentrations favoring shell-building organisms while others support different metabolic pathways and ecological strategies. Deep beneath the shallow seas, the collision process continues to influence crustal structure and heat flow patterns. Thermal springs associated with deep circulation of groundwater create local environments where thermophilic bacteria and early multicellular organisms experiment with life at elevated temperatures. These hot spring deposits preserve some of the earliest evidence of complex microbial communities and provide insights into the types of environments that may have supported the origin and early evolution of life. The mineral deposits associated with these thermal systems include siliceous sinters, sulfide precipitates, and evaporite formations that create distinctive geological signatures preserved in the rock record. Volcanic activity related to the continental collision creates ash layers that spread across vast areas of the shallow seas, providing precise time markers that allow correlation of sedimentary sequences across different depositional environments. These volcanic ash deposits contain zircon crystals that preserve radiometric ages with precision, measured in tens of thousands of years, creating a detailed chronological framework for understanding the timing and duration of biological and environmental changes. The ash layers themselves influence marine ecosystems by adding nutrients to the water column and temporarily altering ocean chemistry, sometimes triggering algal blooms or extinction events that are preserved in the fossil record. Tidal processes in these extensive shallow seas create complex patterns of sediment transport and deposition, with tidal ranges that may have exceeded those of any modern marine environment due to the broad continental shelves and restricted oceanic circulation. Tidal bore deposits and intertidal flat sequences preserve evidence of these extreme tidal conditions, with sedimentary structures that indicate current directions, flow velocities, and the duration of subaerial exposure during low tide periods. Only took 4 billion years for a planet to develop the gravitational configuration necessary for complex tidal systems. Though the precise mechanics of tidal energy dissipation in shallow epicontinental seas remain subjects of active research in sedimentology and oceanography, the biological productivity of these shallow seas supports food webs of unprecedented complexity, with energy flow patterns that prefigure the structure of all subsequent marine ecosystems. Primary production occurs both through phytoplankton in the water column and through benthic algae and early vascular plants growing in shallow areas near shore. This primary production supports diverse communities of filter feeders, grazers, and predators, creating trophic structures that will persist with only minor modifications throughout the remainder of Earth's history. The Hercynian suture welds the final pieces of the supercontinent puzzle as Gondwana's northern edge presses against the growing Laurussia, with forces that reshape the planet's surface geology. This collision represents the culmination of hundreds of millions of years of continental drift, the moment when scattered fragments of ancient crust finally unite into a single massive landmass that will dominate Earth's geography for the next 100 million years. The suturing process occurs along a zone of compression that extends for thousands of kilometers, creating mountain ranges, metamorphic belts, and igneous complexes that will persist long after the supercontinent itself has fragmented and dispersed. Along the collision zone, the oceanic crust that once separated Gondwana from Laurussia disappears entirely into subduction zones, carrying with it the fossilized remains of entire marine ecosystems that evolved and flourished on seafloors destined for destruction. The final closure of these ocean basins eliminates deep marine environments that had existed for hundreds of millions of years, fundamentally altering global ocean circulation patterns and triggering climatic changes that affect the entire planet. The process unfolds with the inevitability of planetary mechanics, each continental fragment following trajectories determined by mantle convection patterns, magnetic field configurations, and the gravitational interactions between lithospheric plates moving at rates measured in centimeters per year, deep beneath the collision zone. The descending oceanic slabs generate massive volumes of magma as they encounter the heat and pressure conditions of the upper mantle. These magmas rise through the overlying continental crust, creating extensive volcanic belts and granitic batholiths that will become some of the most distinctive geological features of the assembled supercontinent. The intrusive rocks carry with them chemical signatures that reveal the composition of their source regions, isotopic fingerprints that allow modern geologists to reconstruct the geometry and timing of the collision process with remarkable precision. Individual zircon crystals within these granites preserve uranium-lead ages that can be measured to within a few million years, creating a detailed chronological framework for understanding the assembly of Pangaea. Scientists debate the exact mechanisms that drove this final phase of continental assembly, the specific forces that brought Gondwana and Laurussia together across thousands of kilometers of intervening ocean. Paleomagnetic data suggests complex patterns of continental rotation and translation, with individual terrains following curved paths as they were swept up in the collision process. The magnetic signatures preserved in these rocks reflect not only the ancient positions of continents relative to magnetic poles, but also the local magnetic anomalies created by ore deposits, volcanic rocks, and metamorphic minerals that acquired their magnetization under specific temperature and pressure conditions. Only took 400 million years for geologists to develop the analytical techniques necessary to decode these magnetic archives. Though the interpretation of paleomagnetic data from highly deformed rocks remains challenging, even with modern laboratory methods. The collision creates metamorphic pressures and temperatures that transform existing rocks into mineral assemblages never before seen in Earth's crustal history. Ultra-high-pressure metamorphism generates coesite and diamond-bearing rocks that indicate burial to depths of more than 100 kilometers, conditions normally associated with the upper mantle rather than the continental crust. These exotic mineral assemblages form when crustal rocks are dragged down into subduction zones and then rapidly exhumed back to the surface, preserving textural and chemical evidence of their journey into the planet's interior. The formation of these ultra-high-pressure rocks requires collision velocities and exhumation rates that challenge conventional models of continental tectonics, suggesting that the assembly of supercontinents involves processes that operate faster and more violently than previously imagined. Fold and thrust belts develop along the collision zone as the continental margins accommodate hundreds of kilometers of horizontal shortening through complex systems of faulting and folding. Individual thrust sheets may travel distances of 50 to 100 kilometers from their original positions, carrying with them distinctive rock formations that allow geologists to reconstruct the pre-collision geography of the continental margins. The deformation process creates systematic patterns of structural orientation, with fold axes and fault planes aligned according to the direction of maximum compression during the collision. These structural patterns persist for hundreds of millions of years after the collision has ended, influencing the orientation of river valleys, the development of ore deposits, and the susceptibility of different rock units to weathering and erosion. The suturing process eliminates the deep ocean basins that once separated the continents, fundamentally altering the planet's hydrological and climatic systems. Ocean circulation patterns that had persisted for hundreds of millions of years disappear as seaways close, and continental barriers redirect oceanic currents into new configurations. The loss of deep marine environments affects global biogeochemical cycles, particularly the cycling of carbon, nitrogen, and phosphorus between oceanic and continental reservoirs. These changes trigger extinctions among marine organisms adapted to deep water environments while creating new opportunities for shallow water and terrestrial species to diversify and expand their geographical ranges. Strange that the collision should generate both destruction and creation simultaneously, with mountain building processes creating new topographic relief even as erosion begins to wear down the rising peaks. The balance between uplift and denudation determines the ultimate height and longevity of the collision-related mountain ranges, with some peaks reaching elevations comparable to the modern Himalayas, while others are reduced to low hills within a few tens of millions of years. The erosional products derived from these mountains spread across vast areas of the adjacent continental interiors, creating thick sequences of arcosic sandstones and conglomerates that preserve detailed records of the timing and intensity of mountain-building episodes. Volcanic activity associated with the collision creates distinctive rock formations that reflect the complex magmatic processes operating during continental suturing. Calc-alkaline volcanic arcs develop above subduction zones, producing andesitic and dacitic lavas with chemical compositions intermediate between oceanic basalts and continental granites. These volcanic rocks preserve evidence of the subduction process in their trace element signatures, with distinctive patterns of enrichment and depletion that reflect the involvement of subducted oceanic crust and sediments in magma generation. The volcanic activity itself occurs in episodic pulses related to changes in subduction rate, collision geometry, and the thermal structure of the descending oceanic slabs. Ore deposits associated with the collision process create some of the richest mineral concentrations in Earth's crustal history. Hydrothermal systems driven by magmatic heat and metamorphic fluids transport and concentrate metals in fault zones. Contact aureoles and other structural and lithological environments favorable for ore deposition. Gold, copper, lead, and zinc deposits formed during this period will become economically important resources for future civilizations. Their formation requiring the precise combination of source rocks, transport mechanisms, and depositional environments that occur only during major continental collision events. The ore-forming processes operate on timescales of thousands to millions of years, with individual mineral deposits recording multiple episodes of fluid flow and metal precipitation. The biological consequences of continental suturing extend far beyond the immediate effects of habitat destruction and climatic change. The elimination of oceanic barriers allows previously isolated continental biotas to intermingle for the first time, creating opportunities for competitive interaction, hybridization, and evolutionary innovation that would not have been possible while the continents remained separated. Some lineages undergo rapid adaptive radiation as they encounter new environmental conditions and ecological niches, while others experience extinction as they fail to compete successfully with immigrants from other continental regions. The fossil record preserves evidence of these biological exchanges in the form of mixed fossil assemblages that contain species derived from multiple continental sources. Climate patterns across the newly assembled supercontinent reflect the complex interactions between continental configuration, ocean circulation, and atmospheric dynamics. The interior regions of Pangaea begin to experience continental climate conditions for the first time, with temperature and precipitation patterns that differ markedly from the more moderate oceanic climates that had characterized the individual continental fragments. Seasonal temperature variations become more extreme as continental interiors lose the moderating influence of nearby oceans, while precipitation patterns shift as mountain ranges begin to create rain shadows and orographic effects that influence the distribution of moisture across the landscape. Deep crustal structure beneath the collision zone reveals evidence of the complex processes that operated during continental suturing. Seismic reflection profiles show thick zones of highly reflective material that may represent partially molten rock, subducted oceanic crust, or zones of intense shearing and fluid circulation. These deep structural features persist for hundreds of millions of years after the collision has ended, creating zones of weakness that influence the location and orientation of future tectonic activity. Only took 4 billion years for a planet to develop the crustal recycling mechanisms that allow continental collision to create permanent structural heterogeneities in the lithosphere. Though the long-term evolution of these deep crustal features remains poorly understood, even with modern geophysical techniques, the completed suture represents a permanent scar in the Earth's crust, a zone of structural and compositional complexity that records the violent processes involved in supercontinent assembly. This scar will influence geological processes for hundreds of millions of years into the future, providing pathways for magma intrusion, zones of weakness for fault development, and sources of distinctive rock types that will be recycled through multiple episodes of erosion, transport, and deposition as the supercontinent cycle continues its endless progression through deep time. Pangaea stands assembled complete for the first time in Earth's history. Nearly all continental crust united within a single massive landmass that stretches from pole to pole and dominates the planet's surface geography. The supercontinent spans roughly one-third of Earth's circumference, creating a continental mass so vast that its interior regions lie more than 1,000 kilometers from the nearest ocean. This unprecedented concentration of crustal material fundamentally alters the planet's heat budget, ocean circulation patterns, and atmospheric dynamics in ways that will influence climate and biological evolution for the next 100 million years. The assembled supercontinent exhibits a complex internal structure reflecting its origins as a collage of smaller continental fragments, welded together by collision and suturing processes. Ancient cratonic cores, some dating back more than 3 billion years, form stable nuclei around which younger terrains and volcanic arcs have been accreted through successive episodes of continental growth. The boundaries between these different crustal provinces remain visible in the geological record as zones of metamorphism, igneous intrusion, and structural deformation that preserve evidence of the collision events that assembled the supercontinent. Each province carries its own distinctive rock types, isotopic signatures, and structural orientations, creating a complex mosaic of geological terrains within the unified continental mass. Scientists reconstruct the configuration of Pangaea through careful analysis of paleomagnetic data, fossil distributions, and the geometric relationships between mountain belts and sedimentary basins. The supercontinent appears to have been roughly C-shaped, with a large embayment known as the Tethys Sea penetrating deep into the eastern margin. This configuration creates a complex coastline with numerous peninsulas, islands, and shallow epicontinental seas that provide diverse marine habitats along the continental margins. The western coast faces the vast Panthalassa Ocean, a body of water that covers more than two-thirds of the planet's surface and contains oceanic crust that will eventually be entirely consumed by subduction as the supercontinent cycle continues. The gravitational effects of concentrating so much continental mass in a single location influence mantle convection patterns beneath the supercontinent. Thermal insulation provided by the thick continental lithosphere restricts heat loss from the underlying mantle, creating a zone of elevated temperatures that may extend hundreds of kilometers into the Earth's interior. This thermal anomaly affects the buoyancy and flow patterns of mantle material, potentially contributing to the eventual breakup of the supercontinent as rising mantle plumes seek pathways to the surface through zones of crustal weakness. Only took 4.5 billion years for a planet to assemble a supercontinent massive enough to influence deep mantle processes. Though the feedbacks between surface tectonics and mantle dynamics remain subjects of active research. Strange that such a massive continental assembly should be inherently unstable. Yet the same mantle convection processes that drove the continental fragments together also contain the seeds of future fragmentation. The supercontinent's configuration creates a thermal boundary layer between the continental lithosphere and the underlying asthenosphere, a zone where temperature gradients and chemical differences drive convective instabilities that will eventually lead to continental rifting and dispersal. The precise timing and geometry of this future breakup remain determined by the complex interplay between thermal evolution, stress accumulation, and the inherited structural weaknesses created during the assembly process. Ocean circulation around Pangaea follows patterns unlike anything in the modern world, with a single continuous oceanic circulation system wrapping around the supercontinent and connecting polar and equatorial regions through massive current systems. The Panthalassa Ocean develops its own distinctive circulation patterns, with vast subtropical gyres and equatorial current systems that transport heat and nutrients across oceanic distances unmatched in Earth's subsequent history. These circulation patterns influence global climate by determining the distribution of heat between different latitude bands and by controlling the upwelling of nutrient-rich deep water in coastal regions around the supercontinent. The biological consequences of supercontinent assembly extend across both marine and terrestrial environments. Marine organisms that had evolved in isolation on different continental margins suddenly encounter competitors and predators from other biogeographic provinces, leading to complex patterns of extinction, migration, and adaptive radiation. Some lineages benefit from the expanded geographical ranges made possible by continental connection, while others suffer from increased competition and environmental change. The terrestrial biota experiences similar disruptions as previously separated ecosystems come into contact for the first time, creating opportunities for biological exchange that would not have been possible while the continents remained dispersed. Atmospheric circulation patterns over Pangaea develop characteristics that reflect the supercontinent's enormous size and complex topography. Monsoon systems driven by seasonal heating and cooling of the continental interior create precipitation patterns that vary dramatically between summer and winter months. The interior regions experience extreme continental climate conditions, with hot summers, cold winters, and limited precipitation due to their distance from oceanic moisture sources. Coastal regions maintain more moderate climates, but even these areas experience greater seasonal temperature variations than comparable latitudes in more dispersed continental configurations. The sedimentary record from this period preserves evidence of the environmental conditions that characterize the fully assembled supercontinent. Red bed formations indicate arid and semi-arid conditions across vast areas of the continental interior, while evaporate deposits suggest the presence of closed basins where evaporation exceeded precipitation. Coal deposits along the equatorial margins record the existence of extensive peat swamps and tropical forests, while glacial deposits near the poles provide evidence for ice sheet development in high-latitude regions of the supercontinent. These different sedimentary facies create a detailed paleoclimatic record that allows reconstruction of environmental conditions across different parts of Pangaea. Volcanic activity associated with the final assembly of Pangaea creates distinctive igneous provinces that reflect the complex thermal and tectonic processes operating within the supercontinent. Large igneous provinces develop in response to mantle plume activity, creating flood basalt sequences that cover vast areas with layers of volcanic rock hundreds of meters thick. These volcanic episodes release enormous quantities of gases into the atmosphere, including carbon dioxide, sulfur dioxide, and other compounds that influence global climate and atmospheric chemistry. The timing and duration of these volcanic events can be precisely determined through radiometric dating, providing critical constraints on the relationship between igneous activity and environmental change. Deep crustal structure beneath Pangaea reveals evidence of the complex processes that operated during supercontinent assembly. Thick zones of highly deformed and metamorphosed rock extend to depths of 30 to 40 kilometers, indicating the amount of crustal thickening that occurred during continental collision. These deep structural features create zones of weakness that will influence the location and orientation of future rifting when the supercontinent eventually begins to break apart. The preservation of these structures requires rapid cooling and stabilization of the continental lithosphere, processes that depend on the thermal evolution of the underlying mantle and the efficiency of heat loss through conduction and convection. Mineral deposits associated with supercontinent assembly create some of the richest ore concentrations in Earth's history. Hydrothermal systems driven by the cooling of large igneous intrusions transport and concentrate metals in structural and lithological environments, favorable for ore deposition. The complex geological relationships created by continental collision provide multiple opportunities for fluid circulation, chemical reaction, and mineral precipitation, resulting in ore deposits that will become economically important resources for future civilizations. The formation of these deposits requires precise combinations of source rocks, transport mechanisms, and depositional environments that occur only during major episodes of continental assembly. The completed supercontinent represents a unique configuration in Earth's tectonic history, a moment when nearly all continental crust exists within a single landmass surrounded by a global ocean. This configuration will persist for approximately 50 million years before the first signs of rifting begin to appear along zones of crustal weakness inherited from the assembly process. Only took 4 billion years for plate tectonic processes to assemble a supercontinent of this magnitude. Though similar continental configurations may have existed earlier in Earth's history during periods for which the geological record has been largely destroyed by subsequent tectonic activity. The gravitational stability of such a massive continental assembly depends on the balance between the buoyancy forces that keep the continental lithosphere floating on the underlying mantle and the thermal forces that drive convective circulation in the Earth's interior. This balance remains delicate throughout the supercontinent's existence, with small changes in mantle temperature, crustal thickness, or thermal conductivity potentially triggering the rifting processes that will eventually lead to continental dispersal. The assembled supercontinent thus represents both the culmination of one supercontinent cycle and the beginning of the next, a temporary configuration that preserves evidence of past continental assembly while containing the structural and thermal conditions necessary for future fragmentation. The interior desert expanse of Pangaea transforms vast continental regions into the largest arid system Earth has ever known, a landscape of sand seas and rocky badlands that stretches across thousands of kilometers of continental interior, isolated from oceanic moisture sources. These deserts develop not from any single climatic cause, but from the complex interaction of continental size, atmospheric circulation patterns, and topographic barriers that combine to create conditions of extreme aridity across much of the supercontinent's heartland. The desert formation process operates according to fundamental principles of atmospheric physics, with air masses losing their moisture content as they travel across the enormous continental distances necessary to reach the interior regions. Atmospheric circulation over the supercontinent creates semi-permanent high-pressure systems that suppress precipitation and enhance evaporation rates across the continental interior. Descending air masses associated with these high-pressure zones become progressively warmer and drier as they approach the surface, creating atmospheric conditions that can absorb rather than release moisture, even when relative humidity levels appear significant. The seasonal migration of these pressure systems follows the annual cycle of solar heating, creating distinct wet and dry seasons in some regions while maintaining year-round aridity in others. The precise boundaries between different climatic zones shift gradually over thousands of years in response to changes in atmospheric circulation patterns, ocean temperatures, and the configuration of topographic barriers around the continental margins. Sand dune systems develop across vast areas of the interior deserts, creating aeolian landscapes that preserve detailed records of ancient wind patterns and sediment transport processes. Individual sand grains undergo multiple cycles of erosion, transport, and deposition as they migrate across the desert surfaces. their shapes and surface textures recording the mechanical processes that operate during aeolian transport. Barchan dunes, linear dunes, and star dunes form in response to different wind regimes and sediment supply conditions. Each dune type creating its own distinctive sedimentary structures that can be recognized in the rock record, millions of years after the original dunes have been buried and lithified. Only took 3 billion years for a planet to develop the atmospheric conditions necessary for large-scale aeolian processes. Though the mechanics of sand grain transport remain subjects of active research in sedimentology and fluid dynamics, scientists puzzle over the exact extent and intensity of Pangaean aridity, the precise geographic boundaries of the desert regions, and the degree of environmental stress experienced by organisms living in these extreme conditions. Paleosol studies reveal evidence of calcrete and gypcrete formation, soil horizons dominated by carbonate and sulfate minerals that indicate very low precipitation rates and high evaporation potentials. However, the interpretation of these paleosol indicators remains complex, complicated by the effects of diagenesis, groundwater fluctuations, and the possibility that some apparent desert deposits actually formed in coastal Sabkha environments, rather than true continental interiors. The fossil record from these regions remains sparse, limited largely to trackways and rare skeletal remains that provide only fragmentary evidence of the biological communities that managed to survive in these harsh environments. Ephemeral lake systems develop in topographic depressions across the desert regions, filling with water during brief rainy seasons and then evaporating completely during extended dry periods. These paleolakes leave behind deposits of evaporate minerals, including halite, gypsum, and more exotic compounds such as trona and mirabilite that form only under specific combinations of temperature, salinity, and chemical composition. The evaporite sequences preserve detailed records of the chemical evolution of these temporary water bodies, with different mineral phases precipitating in systematic order as evaporation concentrates the dissolved salts. Some of these evaporite deposits reach thicknesses of hundreds of meters, indicating repeated cycles of lake filling and desiccation over millions of years. Flash flood deposits create distinctive sedimentary sequences in the desert regions, preserving evidence of the extreme precipitation events that occasionally occur even in the most arid environments. These flood deposits consist of poorly sorted gravels and sands that were transported rapidly across desert surfaces during brief but intense storm events, creating alluvial fans and ephemeral stream channels that remain dry for years or decades between flooding episodes. The sedimentary structures preserved in these deposits indicate very high flow velocities and sediment concentrations, with debris flows and hyperconcentrated flows dominating the transport processes rather than the normal water flows that characterize humid region streams. Groundwater systems beneath the desert regions create localized oases, where springs and seeps support small communities of drought-adapted organisms. These groundwater sources depend on precipitation that falls in distant mountain ranges and then flows through subsurface aquifer systems that may extend hundreds of kilometers from their recharge areas. The groundwater itself carries dissolved minerals leached from the rocks through which it flows, creating water chemistry conditions that vary significantly between different aquifer systems and hydrogeological environments. Some groundwater systems discharge as hot springs, indicating circulation through deep crustal rocks where geothermal heating raises water temperatures well above surface ambient conditions. Strange that such extreme aridity should coexist with evidence of episodic flooding and lake formation. Yet the desert regions experience highly variable precipitation patterns, with most rainfall concentrated in brief, intense events separated by extended dry periods. The coefficient of variation in annual precipitation may exceed 100% in some areas, meaning that the standard deviation in rainfall amounts equals or exceeds the long-term average precipitation. This extreme variability creates environmental conditions that challenge the survival strategies of desert organisms, requiring adaptations for both drought tolerance and flood survival within the same ecological communities. Biological adaptations to desert conditions include physiological, morphological, and behavioral modifications that allow organisms to survive in environments where water availability, temperature extremes, and nutrient scarcity create multiple forms of environmental stress simultaneously. Some organisms develop water storage capabilities in specialized tissues, while others evolve efficient kidney function that allows them to concentrate urine and minimize water loss. Behavioral adaptations include burrowing to avoid temperature extremes, nocturnal activity patterns that reduce water loss, and migration strategies that allow organisms to track resource availability across large geographical areas. Soil development in the desert regions follows patterns that differ markedly from those in more humid environments, with physical weathering processes dominating over chemical weathering due to the limited availability of water for mineral dissolution and hydrolysis reactions. Desert soils typically exhibit minimal profile development, with thin A horizons overlying relatively unaltered parent material. Calcic and gypsic horizons form in response to the limited leaching that occurs during brief wet periods, creating subsurface accumulations of carbonate and sulfate minerals that persist for thousands of years. The slow rates of soil formation in arid environments mean that desert soils preserve evidence of environmental conditions extending back much further in time than soils in humid regions. Wind erosion processes in the desert regions create distinctive landforms including yardangs, deflation hollows, and ventifacts that record the direction and intensity of prevailing wind patterns. These erosional features develop over timescales of thousands to millions of years, with different rock types responding to wind abrasion according to their hardness, jointing patterns, and chemical composition. Resistant rock formations create mesas and buttes that rise above the general erosion surface, while weaker rocks are preferentially removed to create valleys and lowlands that channel wind flow and enhance erosional processes. Chemical weathering in the desert regions operates according to different principles than in humid environments, with oxidation and salt weathering playing more important roles than the hydrolysis and carbonation reactions that dominate in areas with abundant water. Salt weathering occurs when dissolved salts precipitate in rock fractures and create pressures sufficient to wedge apart mineral grains and create new fracture systems. The effectiveness of salt weathering depends on the availability of saline groundwater, the porosity and permeability of the rock, and the frequency of wetting and drying cycles that drive salt crystallization and dissolution. Dust storms transport fine-grained sediments across vast distances, creating atmospheric loads of suspended particles that influence regional climate patterns and deposit sedimentary sequences in areas far removed from their source regions. These dust storms may transport material for thousands of kilometers before depositing it in marine environments, where it contributes to deep-sea sedimentary sequences. The mineral composition and grain size characteristics of these dust deposits provide information about their source regions and transport pathways, allowing reconstruction of ancient wind patterns and atmospheric circulation systems. The persistence of desert conditions across the Pangaean interior requires stable atmospheric circulation patterns that maintain high-pressure zones and suppress convective precipitation over vast geographical areas. These circulation patterns depend on the thermal contrast between continental and oceanic regions, the effects of topographic barriers on airflow, and the seasonal migration of pressure systems in response to changes in solar heating. Only took 4 billion years for a planet to develop the continental configurations necessary for such extensive desert formation. Though the detailed relationships between continental size, atmospheric circulation, and aridity remain subjects of ongoing research in paleoclimatology and atmospheric science. Permian life flourishes along Pangaea's coastlines while the interior remains largely barren, creating a sharp dichotomy between the biological richness of marine and coastal environments and the harsh conditions that persist across vast areas of the continental heartland. This geographic pattern of biodiversity reflects the fundamental constraints imposed by water availability, temperature extremes, and nutrient scarcity in the supercontinent's interior regions, where only the most specialized organisms can survive the extreme environmental conditions. The coastal zones, By contrast, support complex ecosystems that represent some of the most diverse biological communities in Earth's history, with marine, terrestrial, and transitional environments creating a mosaic of ecological niches and evolutionary opportunities. Marine ecosystems around Pangaea reach unprecedented levels of complexity and diversity, with extensive reef systems, diverse fish communities, and complex invertebrate assemblages that occupy virtually every available ecological niche in shallow marine environments. Brachiopods achieve their greatest morphological diversity during this period, with hundreds of species exhibiting specialized shell shapes and feeding strategies adapted to specific environmental conditions. Bryozoans form massive colonial structures that compete with corals for space and resources on the seafloor, while crinoids create vast meadows of stalked echinoderms that filter nutrients from the water column with remarkable efficiency. The success of these marine communities depends on stable ocean chemistry, consistent nutrient supply, and the absence of major environmental perturbations that would disrupt the complex ecological relationships between different species. Terrestrial ecosystems along the continental margins support the first truly modern forest communities, with seed plants beginning to dominate over spore-producing species in many environments. Conifers develop sophisticated reproductive strategies that allow them to colonize drier habitats than their fern and lycopsid predecessors, while early flowering plants experiment with new approaches to pollination and seed dispersal. These forest ecosystems support diverse communities of insects, early reptiles, and amphibians that exploit the three-dimensional habitat structure created by complex vegetation. The development of seeds as reproductive structures represents one of the most significant innovations in plant evolution, allowing terrestrial plants to reproduce successfully in environments where free water is not continuously available for sperm transport. Scientists remain uncertain about the exact diversity and composition of Permian terrestrial communities, particularly in the more arid interior regions, where preservation conditions limit the formation and discovery of fossil assemblages. The fossil record from coastal and near-coastal environments provides detailed information about the organisms that lived in these more favorable habitats. But the interior regions remain largely mysterious due to the lack of sedimentary environments suitable for fossil preservation. Trackway evidence suggests that various reptile and amphibian groups were able to penetrate at least the margins of the desert regions. But the nature and extent of these interior ecosystems remain subjects of speculation and ongoing research. Reptilian diversity reaches remarkable levels during the Permian, with numerous lineages experimenting with different approaches to terrestrial life. Therapsids develop increasingly mammal-like characteristics, including differentiated teeth, more efficient jaw mechanics, and possibly even primitive forms of hair and temperature regulation. Some of these early synapsids reach considerable size, with predatory forms achieving body masses comparable to modern large carnivores. The success of these reptilian groups reflects their superior adaptations to terrestrial environments, particularly their more efficient reproductive strategies and improved physiological capabilities for dealing with variable environmental conditions. Coastal wetland environments create transitional zones where marine and terrestrial ecosystems interact, supporting unique communities of organisms adapted to fluctuating salinity, periodic flooding, and variable substrate conditions. These marginal environments serve as evolutionary laboratories where innovations developed in one environment can be tested and refined under the selective pressures imposed by another. Early tetrapods continue to diversify in these transitional habitats, with some lineages becoming increasingly terrestrial, while others remain closely tied to aquatic environments. The complex environmental gradients present in these coastal zones create numerous microhabitats that support specialized communities of plants, invertebrates, and vertebrates. Strange that such biological richness should coexist with the extreme desolation of the continental interior. Yet the contrast reflects the fundamental importance of water availability in determining the distribution and diversity of life on land. The coastal regions benefit from oceanic moisture sources, more moderate temperature regimes, and the nutrient inputs provided by rivers draining from the continental margins. While the interior regions lack access to these essential resources, this geographic pattern of biodiversity will persist throughout much of Earth's subsequent history, with coastal and riparian environments consistently supporting more diverse biological communities than arid continental interiors. Insect communities achieve remarkable diversity and ecological complexity during the Permian, with numerous lineages developing specialized feeding strategies, complex life cycles, and sophisticated behavioral adaptations. Some insects reach enormous sizes, taking advantage of the elevated oxygen concentrations that characterize Permian atmospheres. These large insects include predatory forms with wingspans exceeding half a meter, as well as herbivorous species that exploit the expanding diversity of seed plants. The coevolutionary relationships between insects and plants during this period establish ecological patterns that will persist throughout the remainder of terrestrial evolutionary history. Freshwater environments along the continental margins support diverse communities of fish, amphibians, and aquatic invertebrates that exploit the resources available in rivers, lakes, and wetland systems. These freshwater ecosystems serve as corridors for biological dispersal, allowing organisms to migrate along river systems and colonize new habitats as environmental conditions change. The chemical composition of freshwater during this period differs from modern conditions due to different weathering patterns, atmospheric composition, and the absence of certain biological processes that would later become important in aquatic biogeochemical cycles. Soil communities in the coastal regions develop increasing complexity as terrestrial ecosystems mature and diversify. Fungi, bacteria, and early arthropods create intricate networks of ecological relationships that enhance nutrient cycling, improve soil structure, and support the productivity of terrestrial plant communities. These soil ecosystems represent some of the first truly complex terrestrial food webs, with multiple trophic levels and sophisticated chemical communications between different organisms. The development of complex soil communities requires millions of years of coevolutionary interaction between plants, microorganisms, and soil fauna. Pollination systems become increasingly sophisticated as flowering plants begin to diversify, and insects develop specialized morphologies and behaviors for nectar and pollen collection. These plant-pollinator relationships represent some of the earliest examples of highly co-evolved mutualistic interactions in terrestrial ecosystems, with both plants and insects benefiting from the exchange of resources and reproductive services. The evolution of these pollination systems contributes to the rapid diversification of both flowering plants and insects during the later Permian and subsequent periods. Predator-prey relationships in Permian ecosystems become increasingly complex as different vertebrate groups develop specialized hunting strategies and defensive adaptations. Arms races between predators and their prey drive morphological innovation and behavioral evolution, creating feedback loops that enhance the diversity and ecological complexity of terrestrial communities. These evolutionary dynamics operate over timescales of millions of years, with gradual changes in morphology and behavior accumulating to create the sophisticated ecological relationships that characterize mature terrestrial ecosystems. Seasonal climate patterns along Pangaea's margins create temporal heterogeneity that adds another dimension to ecological complexity. With different species active during different parts of the year and various life history strategies adapted to take advantage of seasonal resource availability, migration patterns develop as organisms learn to track resources across both geographical and temporal gradients, creating large-scale patterns of animal movement that connect distant ecosystems and enhance gene flow between populations. Only took 300 million years for terrestrial ecosystems to develop the complexity necessary for large-scale seasonal migrations. Though the evolution of migration behavior requires sophisticated navigational abilities and physiological adaptations for long-distance movement, the productivity of coastal marine environments supports large populations of organisms that serve as the base of complex food webs extending into both marine and terrestrial environments. Nutrients exported from marine systems fertilize coastal terrestrial ecosystems through the activities of seabirds, marine mammals, and anadromous fish that transport marine-derived nutrients to terrestrial habitats. These cross-ecosystem nutrient subsidies enhance the productivity and diversity of coastal terrestrial communities, creating positive feedbacks that contribute to the overall biological richness of continental margin environments. The great dying approaches as Siberian flood basalts begin their massive eruptions, slowly poisoning the atmosphere and oceans around the supercontinent with volcanic gases that will trigger the most severe extinction event in Earth's history. These eruptions unfold over hundreds of thousands of years, each individual eruption lasting days to weeks, but collectively releasing volumes of lava sufficient to cover an area the size of modern Europe with basaltic rock hundreds of meters thick. The volcanic activity represents one of the largest igneous events in Earth's geological record, involving the eruption of more than 4 million cubic kilometers of basaltic magma from a mantle plume that rises from the core mantle boundary beneath the Siberian continent. The eruption process begins with the intrusion of massive dike swarms and sill complexes that carry magma from deep mantle sources through the overlying continental crust. These intrusive rocks interact chemically with the sedimentary and metamorphic rocks of the Siberian crust, particularly with coal beds, evaporate deposits, and carbonate formations that release additional gases when heated by the intruding magma. The interaction between basaltic magma and crustal rocks generates complex mixtures of volcanic gases, including carbon dioxide, sulfur dioxide, hydrogen sulfide, and chlorine compounds that create atmospheric conditions unlike anything in Earth's previous history. The gas release occurs through both direct volcanic emissions and through the thermal decomposition of crustal rocks, creating a sustained input of toxic compounds to the atmosphere that persists for hundreds of thousands of years. Scientists estimate that the Siberian eruptions released between 10 and 40,000 gigatons of carbon dioxide into the atmosphere, quantities sufficient to increase atmospheric carbon dioxide concentrations by factors of 3 to 10 above pre-eruption levels. The carbon dioxide emissions create severe greenhouse warming that raises global temperatures by 8 to 15 degrees Celsius, transforming Earth's climate system and creating environmental conditions that exceed the tolerance limits of most existing organisms. The warming occurs rapidly on geological timescales, with most of the temperature increase occurring within a few thousand years of the onset of major volcanic activity. Only took 250 million years for volcanic activity to reach the scale necessary to disrupt global environmental systems, though the precise mechanisms linking volcanism to mass extinction remain subjects of active research. Sulfur dioxide emissions from the eruptions create acid rain conditions that acidify both terrestrial and marine environments, while also forming atmospheric aerosols that temporarily cool the planet through increased reflection of solar radiation. This cooling effect operates for only a few years after each major eruption, creating short-term climate fluctuations superimposed on the longer-term greenhouse warming caused by carbon dioxide accumulation. The acid rain dissolves carbonate minerals in soils and sediments, releasing additional carbon dioxide to the atmosphere and creating positive feedback loops that amplify the greenhouse warming effect. Marine environments experience particularly severe acidification, as sulfuric acid combines with seawater to create conditions that dissolve the calcium carbonate shells and skeletons of marine organisms. Ocean chemistry changes dramatically as the volcanic emissions alter the pH oxygen content and trace element composition of seawater. Hydrogen sulfide released by the eruptions creates reducing conditions in marine environments, while the breakdown of organic matter in oxygen-depleted waters generates additional hydrogen sulfide through bacterial sulfate reduction. These chemical changes create toxic conditions for most marine organisms, particularly those that rely on calcium carbonate for shell or skeleton construction. The ocean chemistry changes propagate through marine food webs, affecting primary producers, filter feeders, and predatory organisms and cascading extinction events that eliminate entire marine ecosystems. Strange that volcanic activity, which had previously created new habitats and supported biological diversity through the formation of islands and volcanic soils, should become the agent of nearly total biological destruction. The difference lies in the scale and duration of the Siberian eruptions, which exceed the capacity of Earth's environmental systems to absorb and neutralize the volcanic emissions. Previous volcanic events had been smaller in scale or shorter in duration, allowing biological and geological systems to adapt or recover from the environmental perturbations. The Siberian event represents a threshold crossing, a point at which volcanic emissions overwhelm the buffering capacity of the atmosphere and oceans. Terrestrial ecosystems experience severe stress as acid rain damages plant tissues. Soil acidification reduces nutrient availability, and extreme temperature fluctuations exceed the tolerance limits of most organisms. Forest ecosystems collapse across vast areas as trees are killed by acid rain and extreme temperatures, while soil communities are disrupted by chemical changes that affect nutrient cycling and decomposition processes. The loss of vegetation cover accelerates erosion and reduces the land surface's ability to moderate local climate conditions, creating positive feedback loops that amplify the environmental deterioration. Some organisms survive in refugia where local conditions remain favorable, but these refugia become increasingly isolated as the environmental crisis intensifies. Marine ecosystems suffer even more severe disruption than terrestrial systems, with extinction rates exceeding 90% for many groups of marine organisms. Reef ecosystems collapse entirely as corals and other carbonate-secreting organisms are unable to maintain their skeletons in acidified seawater. Planktonic communities are devastated by the combined effects of ocean acidification, warming, and toxicity, disrupting marine food webs and eliminating the primary productivity that supports most marine ecosystems. Deepwater environments become anoxic as decomposing organic matter consumes available oxygen, creating dead zones where only anaerobic bacteria can survive. The extinction process unfolds over several 100,000 years, with multiple pulses of environmental deterioration corresponding to different phases of volcanic activity. Some organisms survive the initial impacts only to succumb to later environmental changes, while others persist through most of the crisis before finally being eliminated by the cumulative effects of prolonged environmental stress. The extinction selectivity shows complex patterns, with some groups experiencing complete elimination while others suffer severe losses but retain enough survivors to eventually recover and diversify. Body size, metabolic rate, and habitat specialization all influence survival probability. But the severity of the environmental crisis means that even the most resilient organisms face significant extinction risk. Recovery from the extinction event requires millions of years as surviving organisms slowly recolonize empty habitats and evolve new adaptations to post-extinction environmental conditions. The biological communities that emerge from the recovery process differ fundamentally from those that existed before the extinction, with new evolutionary innovations and ecological relationships that reflect the changed environmental conditions of the post-extinction world. Some ecological niches remain empty for millions of years before being filled by newly evolved organisms, while others are occupied by survivors that undergo rapid evolutionary change in response to reduced competition and new environmental opportunities. Sedimentary sequences deposited during the extinction interval preserve detailed records of the environmental changes that occurred during this critical period in Earth's history. Organic carbon isotope ratios record the massive input of volcanic carbon to the atmosphere, while sulfur isotope signatures reflect the atmospheric processing of volcanic sulfur emissions. Trace element concentrations in marine sediments provide evidence of ocean chemistry changes, and the fossil record documents the biological responses to environmental crisis. These sedimentary archives allow scientists to reconstruct the timing, magnitude, and environmental consequences of the Siberian eruptions with remarkable precision. The genetic consequences of the extinction extend far beyond the immediate loss of biodiversity, with surviving populations experiencing severe bottlenecks that reduce genetic diversity and eliminate evolutionary lineages that had persisted for hundreds of millions of years. The loss of genetic diversity affects the evolutionary potential of surviving groups, influencing their ability to adapt to changing environmental conditions and limiting the range of evolutionary innovations available for future diversification. Some lineages never recover their pre-extinction diversity levels, while others undergo evolutionary radiations that eventually restore ecosystem complexity and biological richness. Geochemical cycles are fundamentally altered by the extinction event, with changes in weathering patterns, erosion rates, and biological productivity creating new equilibrium conditions for the cycling of carbon, sulfur, phosphorus, and other essential elements. The disruption of terrestrial vegetation reduces the efficiency of chemical weathering and allows increased atmospheric carbon dioxide concentrations to persist for millions of years. Marine productivity remains low for extended periods due to the elimination of many primary producer groups and the disruption of nutrient cycling processes. Only took 250 million years for life to create global biogeochemical cycles, complex enough to be severely disrupted by volcanic activity. Though the recovery and re-establishment of these cycles requires millions of years of biological and geological evolution, Triassic recovery unfolds across millions of years as life rebounds from near extinction, while the first hairline cracks appear in Pangaea's lithospheric foundation, marking the beginning of the end for the supercontinent that had dominated Earth's geography for more than 50 million years. The recovery process operates simultaneously across biological and geological systems, with surviving organisms slowly recolonizing empty habitats while deep crustal processes begin to generate the thermal and mechanical stresses that will eventually tear the supercontinent apart. These parallel processes of biological renewal and continental fragmentation create the environmental context for the next major phase of Earth's evolutionary and geological history. Biological recovery begins with the expansion of disaster taxa, opportunistic organisms that can thrive in the simplified ecosystems that emerge immediately after the extinction event. These early colonizers typically possess rapid reproductive rates, broad environmental tolerances, and simple ecological requirements that allow them to exploit the abundant resources available in depopulated habitats. Small-bodied organisms generally recover faster than large-bodied species, while generalist feeders have advantages over specialized forms that depend on specific food sources or habitat conditions. The recovery process follows predictable ecological patterns, with primary producers reestablishing themselves first, followed by herbivores, and finally by carnivores and other higher-level consumers. Marine ecosystems show the earliest signs of recovery as ocean chemistry gradually returns to conditions more favorable for shell-building organisms and complex food webs. Small gastropods and bivalves begin to diversify and expand their geographical ranges, while brachiopods and other filter-feeding organisms slowly recolonize shallow marine environments. The recovery of marine primary productivity requires the reestablishment of planktonic communities, a process that depends on the gradual improvement of ocean chemistry and the availability of nutrients released by the breakdown of pre-extinction biomass. Reef ecosystems remain largely absent for millions of years, with carbonate platforms dominated by simple microbial communities rather than the complex colonial organisms that had characterized Permian reefs. Terrestrial recovery proceeds more slowly than marine recovery due to the complex requirements for soil formation, plant community establishment, and the reconstruction of terrestrial food webs. Early Triassic plant communities consist largely of ferns, lycopsids, and other spore-producing groups that can rapidly colonize disturbed habitats and tolerate poor soil conditions. Seed plants recover more gradually, with conifers and early flowering plants requiring stable environmental conditions and well-developed soils for successful establishment. The reestablishment of forest ecosystems requires millions of years as plant communities slowly modify soil chemistry, create microhabitat diversity, and provide the three-dimensional habitat structure necessary for complex animal communities. Scientists debate the precise timing and causes of early Triassic rifting, the initial formation of extensional structures that will eventually lead to continental breakup. Thermal modeling suggests that the thick continental lithosphere of Pangaea creates insulation effects that elevate mantle temperatures beneath the supercontinent, generating thermal expansion and mechanical stresses that weaken the continental crust. The rifting process begins with the formation of small grabens and half-grabens, extensional basins that accommodate modest amounts of crustal stretching while preserving evidence of the early stages of continental fragmentation. These early rift structures follow zones of crustal weakness, inherited from the collision events that assembled the supercontinent, particularly the suture zones where different continental fragments were welded together during Pangaea's formation. Strange that continental assembly should contain the seeds of its own destruction. Yet the same thermal processes that drive mantle convection and continental drift also create the conditions necessary for supercontinent breakup. The concentration of continental material in a single landmass disrupts normal patterns of mantle heat loss, creating thermal anomalies that generate buoyancy forces capable of initiating crustal extension and rifting. The process operates according to the same fundamental principles that govern all plate tectonic activity. But the scale and configuration of a supercontinent create unique boundary conditions that influence the timing, location, and geometry of the breakup process. Volcanic activity associated with early rifting creates distinctive rock formations that preserve evidence of the extensional processes operating beneath the supercontinent. Basaltic dikes and sills intrude along zones of crustal weakness, carrying with them geochemical signatures that reveal the composition and thermal state of the underlying mantle. These early volcanic rocks show evidence of mantle plume activity, with elevated temperatures and distinctive trace element patterns that suggest deep mantle sources for the magmas involved in continental rifting. The volcanic activity itself contributes to crustal heating and weakening, creating positive feedback loops that accelerate the rifting process once it has begun. Climate recovery proceeds in parallel with biological recovery, as atmospheric and oceanic systems gradually adjust to post-extinction conditions. Carbon dioxide concentrations slowly decline from the extreme levels reached during the extinction event, allowing global temperatures to decrease from their peak values while remaining elevated relative to pre-extinction conditions. The climate system exhibits complex oscillations as different feedback mechanisms interact, with ice sheet formation and melting, vegetation changes, and ocean circulation adjustments all contributing to climate variability during the recovery period. Monsoon systems strengthen as continental temperature contrasts increase, creating more pronounced seasonal precipitation patterns that influence biological recovery in different geographical regions. Evolutionary innovations during the Triassic recovery include the development of new morphological, physiological, and ecological adaptations that allow organisms to exploit environmental opportunities created by the extinction event. Archosaurs undergo rapid diversification, giving rise to the first dinosaurs, pterosaurs, and crocodilians that will dominate terrestrial ecosystems for the next 150 million years. These reptilian groups develop increasingly sophisticated adaptations for terrestrial life, including improved locomotory systems, more efficient respiratory mechanisms, and complex social behaviors that enhance their competitive abilities in recovering ecosystems. Marine reptile diversification creates new categories of large predators in ocean environments, with ichthyosaurs, plesiosaurs, and marine crocodiles evolving adaptations for fully aquatic lifestyles. These marine reptiles occupy ecological niches that had been left vacant by the extinction of many fish and cephalopod groups, developing convergent adaptations for swimming, diving, and aquatic feeding that parallel those seen in modern marine mammals. The success of these reptilian groups reflects their superior physiological capabilities and reproductive strategies compared to the amphibians and primitive reptiles that had dominated pre-extinction terrestrial and aquatic environments. Plant evolution during the Triassic includes the continued diversification of seed plants and the early evolution of flowering plants. Although angiosperms remain rare and morphologically simple during this period, conifers achieved their greatest diversity and geographical extent, with different lineages adapting to various climate and soil conditions across the recovering continental landscapes. The coevolution between plants and insects accelerates during this period, with both groups developing increasingly sophisticated relationships involving pollination, herbivory, and chemical defense mechanisms that enhance ecosystem complexity and biological diversity. Sedimentary sequences from the Triassic preserve detailed records of environmental change and biological recovery in both marine and terrestrial environments. Red bed formations indicate continued arid conditions across much of Pangaea's interior, while coastal sequences show evidence of gradually improving marine conditions and increasing biological productivity. Coal deposits become more common toward the end of the Triassic, indicating the reestablishment of extensive wetland ecosystems and the accumulation of sufficient organic matter to form economically important coal seams. The sedimentary record also preserves evidence of the early rifting processes, with fault-bounded basins and volcanic intercalations, providing constraints on the timing and geometry of continental extension. Biogeographic patterns during the Triassic reflect both the continued unity of Pangaea and the early stages of continental fragmentation. Many terrestrial vertebrate groups show cosmopolitan distributions, with similar fossil assemblages found across widely separated parts of the supercontinent. However, subtle provincial differences begin to appear, particularly in marine environments where the early opening of rift basins creates new seaways and barriers to biological dispersal. These biogeographic patterns provide important evidence for the timing and geography of early continental breakup, with the distribution of fossil organisms serving as independent tests of reconstructions based on geological and geophysical data. Paleogeographic reconstructions of Triassic Pangaea show a supercontinent that remains largely intact, but exhibits increasing internal complexity as rift systems begin to develop. The early rift basins create topographic diversity and local climate variations that enhance habitat heterogeneity and support biological diversification. Some rift systems fill with sediments and volcanic rocks, while others develop into marine seaways that allow limited oceanic circulation within the continental interior. The geometric relationships between different rift systems suggests that they represent the early stages of a coordinated breakup process that will eventually separate Pangaea into the continental fragments that characterize the modern world. Magnetic field behavior during the Triassic shows evidence of increased instability and frequent reversals, possibly related to changes in core mantle boundary conditions caused by the thermal effects of supercontinent assembly. These magnetic field variations are preserved in the magnetic signatures of Triassic rocks, providing detailed records of ancient field directions and intensities that can be used to reconstruct continental positions and rotation rates during the early stages of breakup. The magnetic record also preserves evidence of rapid apparent polar wander, reflecting the complex motions of continental fragments as they begin to separate from the main body of Pangaea. Only took 200 million years for life to recover from the most severe extinction event in Earth's history and begin the evolutionary radiations that would lead to modern ecosystem complexity. The recovery process demonstrates the resilience of biological systems and their ability to exploit new environmental opportunities created by major disturbances. However, the recovery also shows the lasting effects of mass extinction, with some ecological roles remaining unfilled for millions of years, and some evolutionary lineages never regaining their pre-extinction diversity and morphological complexity. The Triassic recovery thus represents both an ending and a beginning, marking the close of the Paleozoic era and the dawn of the Mesozoic world that would be dominated by reptiles, flowering plants, and the early stages of continental fragmentation that continues to the present day. The central Atlantic opens as magma wells up through the initial rift between Africa and North America, creating the newest ocean basin through volcanic processes that operate with the patient persistence of geological time. The rifting process begins along zones of crustal weakness inherited from the assembly of Pangaea, where ancient suture zones and fault systems provide pathways for ascending magma and accommodate the extensional stresses that tear the supercontinent apart. Individual volcanic eruptions may last only days or weeks, but the overall process of ocean basin formation requires millions of years as the continental fragments slowly separate and oceanic crust fills the growing gap between them. Basaltic magma rises from the upper mantle through dike swarms and volcanic centers that form roughly parallel lines along the developing rift axis. These volcanic systems tap mantle sources that have been isolated beneath the supercontinent for hundreds of millions of years, creating magmas with distinctive chemical compositions that reflect the long-term evolution of mantle chemistry beneath thick continental lithosphere. The erupted basalts show evidence of interaction with continental crustal rocks, particularly in the early stages of rifting when ascending magmas must traverse thick sequences of sedimentary and metamorphic rocks before reaching the surface. This interaction creates complex hybrid magmas with chemical signatures that preserve evidence of both mantle and crustal contributions to the volcanic process. Scientists reconstruct the geometry and timing of Central Atlantic rifting through careful analysis of magnetic anomaly patterns, radiometric ages of volcanic rocks, and the structural relationships preserved in rift-related sedimentary basins. The rifting appears to have begun simultaneously along multiple segments of the future continental margin, suggesting that the breakup process was controlled by deep mantle processes rather than by the gradual propagation of rifting from a single initiation point. Paleomagnetic data from both sides of the Atlantic provide constraints on the relative motions of the separating continents, while the distribution of flood basalt provinces indicates the locations where mantle plumes intersected the developing rift system. Strange that ocean formation should begin not with dramatic tectonic catastrophe, but with subtle changes in stress fields and magma chemistry that gradually weaken the continental lithosphere over timescales of millions of years. The initial stages of rifting create modest topographic relief and limited volcanic activity, with the most dramatic manifestations of the breakup process occurring only after significant amounts of extension have already been accommodated. The process follows the fundamental principles of lithospheric mechanics, with thermal expansion, mechanical stretching, and magmatic intrusion all contributing to the gradual separation of continental fragments. Sedimentary basins formed during the early stages of rifting preserve detailed records of environmental change and volcanic activity associated with continental breakup. These rift basins accumulate thick sequences of red beds, evaporites, and volcanic rocks that document the transition from continental to marine depositional environments. The sedimentary sequences show evidence of dramatic climate changes as the opening ocean basin begins to influence regional precipitation patterns and temperature regimes. Lacustrine deposits in the early rift basins preserve evidence of large freshwater lakes that developed in topographic depressions created by crustal extension, while evaporate formations indicate periods of restricted marine circulation and high evaporation rates. Volcanic activity intensifies as rifting progresses and the continental lithosphere becomes progressively thinner and weaker. Large igneous provinces develop where mantle plumes intersect the rift system, creating massive outpourings of flood basalts that cover vast areas with volcanic rocks hundreds of meters thick. These volcanic episodes release enormous quantities of gases into the atmosphere, including carbon dioxide, sulfur dioxide, and halogens that influence global climate and atmospheric chemistry. The timing and duration of these volcanic events can be precisely determined through radiometric dating, providing critical constraints on the relationship between mantle dynamics, continental breakup, and environmental change. Ocean floor spreading begins when the continental lithosphere becomes sufficiently extended that ascending basaltic magmas can reach the surface without significant interaction with continental crustal rocks. The transition from continental rifting to oceanic spreading is marked by changes in magma chemistry, volcanic morphology, and structural style that can be recognized in both the geological record and modern rift systems. True oceanic crust forms when spreading rates become high enough to maintain a steady-state thermal structure along the rift axis, creating the characteristic layered structure of oceanic lithosphere with pillow basalts overlying sheeted dikes and gabbroic intrusions. Marine organisms begin to colonize the new ocean basin as seawater floods the developing rift system and establishes connections with the global ocean circulation system. These early marine communities consist largely of opportunistic species that can tolerate the variable environmental conditions characteristic of young ocean basins. Water chemistry in the early Atlantic differs from that of mature ocean basins due to the influence of hydrothermal circulation through young oceanic crust and the input of dissolved minerals from the weathering of newly exposed volcanic rocks. The establishment of stable marine ecosystems requires millions of years as ocean circulation patterns mature and water chemistry stabilizes. Continental margin evolution accompanies ocean basin formation as the separating continents develop the characteristic geological and morphological features of passive margins. Thermal subsidence causes the continental margins to subside below sea level, creating accommodation space for thick sequences of marine sedimentary rocks. These margin sequences preserve detailed records of sea level change, climate variation, and biological evolution as the ocean basin matures and expands. The sedimentary record from continental margins provides some of the most complete archives of Earth's environmental history. With continuous sequences spanning hundreds of millions of years, deep water circulation in the early Atlantic develops gradually as the ocean basin widens and deepens, eventually establishing connections with other ocean basins that allow global thermohaline circulation to reorganize around the new oceanic pathway. The development of deep water circulation has profound effects on global climate, marine productivity, and the distribution of nutrients and dissolved gases between different ocean basins. These circulation changes influence biological evolution by creating new environmental gradients and altering the connectivity between marine provinces that had been isolated during the supercontinent phase. Atmospheric circulation patterns change significantly as the opening Atlantic basin begins to influence global wind systems and precipitation patterns. The presence of a north-south oriented ocean basin in the tropical and subtropical regions creates new moisture sources for continental areas and alters the distribution of heat between different latitude bands. Monsoon systems strengthen as thermal contrasts between continental and oceanic regions increase, while the formation of new topographic barriers associated with rift flanks influences regional wind patterns and orographic precipitation. Biological evolution accelerates as continental fragmentation creates new opportunities for allopatric speciation and adaptive radiation. Populations of terrestrial organisms that had maintained genetic continuity across Pangaea become isolated on different continents, leading to independent evolutionary trajectories that increase global biodiversity. Marine organisms benefit from the creation of new habitats and environmental gradients associated with the developing ocean basin, while the eventual establishment of oceanic circulation allows biological exchange between previously isolated marine provinces. Geochemical cycles are fundamentally altered by the opening of the Atlantic basin, with changes in weathering patterns, erosion rates, and biological productivity creating new equilibrium conditions for the cycling of carbon, sulfur, and other essential elements. The exposure of fresh volcanic rocks to weathering processes creates sinks for atmospheric carbon dioxide, while the development of new marine basins provides additional accommodation space for the burial of organic matter and carbonate sediments. These changes in biogeochemical cycling influence atmospheric composition and global climate over timescales of millions to tens of millions of years. Only took 100 million years for the rifting process to completely separate North America from Africa and create an ocean basin that would eventually span several thousand kilometers in width. The Atlantic Ocean that begins as a narrow seaway comparable to the modern Red Sea will grow to become one of Earth's major ocean basins, influencing global climate, ocean circulation, and biological evolution for the remainder of Earth's history. The opening of the Atlantic represents one of the most significant geographical changes in the planet's recent geological history, transforming Earth from a world dominated by a single supercontinent to the modern configuration of multiple continents separated by interconnected ocean basins. The volcanic rocks and sedimentary sequences formed during Atlantic rifting preserve detailed records of the breakup process that can be studied to understand the fundamental mechanisms of continental fragmentation and ocean basin formation. These records provide insights into the relationships between mantle dynamics, lithospheric mechanics, and surface processes that operate during major episodes of plate tectonic reorganization. The Central Atlantic Magmatic Province represents one of the largest and best preserved examples of flood volcanism associated with continental breakup, offering a natural laboratory for investigating the environmental consequences of massive volcanic events and their role in triggering biological extinction and evolutionary change. Tethys Sea widens and spreads as the ancient seaway between Gondwana fragments expands, allowing tropical currents to flow between separating landmasses and creating new oceanic circulation patterns that will influence global climate for millions of years. This expansion represents one of the most geographically significant aspects of Pangaea's breakup, transforming a relatively narrow embayment into a major ocean basin that extends across much of the tropical and subtropical regions. The widening process operates through seafloor spreading and continental drift, with oceanic crust forming along multiple spreading centers while continental fragments rotate and translate according to the complex geometry of plate motions. The Tethys expansion creates a tropical seaway that fundamentally alters global ocean circulation by providing an east-west connection between different ocean basins in low-latitude regions. This circulation pathway allows the development of strong equatorial current systems that transport heat and nutrients across vast oceanic distances, influencing climate patterns on a global scale. The new circulation patterns enhance biological productivity in tropical marine environments while creating upwelling zones that bring nutrient-rich deep water to the surface where it supports diverse marine ecosystems. These oceanographic changes have cascading effects on terrestrial climate systems, particularly monsoon development and the distribution of precipitation across adjacent continental areas. Marine ecosystems within the expanding Tethys develop characteristics that distinguish them from both the restricted marine environments of the late Paleozoic and the fully oceanic systems of earlier periods. The Tethys becomes a center of marine evolutionary innovation, with numerous groups of organisms undergoing adaptive radiation in response to the new environmental opportunities created by oceanic expansion. Reef ecosystems achieve unprecedented diversity and morphological complexity, with scleractinian corals developing the symbiotic relationships with algae that characterize modern tropical reefs. These coral-algal partnerships allow reef communities to thrive in the oligotrophic waters of tropical oceans, creating massive carbonate buildups that preserve detailed records of ancient environmental conditions. Scientists reconstruct Tethyan paleogeography through integration of paleomagnetic data, biogeographic patterns, and the structural geology of ophiolite complexes that preserve fragments of ancient oceanic crust. The ophiolites provide direct evidence of seafloor spreading processes, with complete sequences from deep oceanic rocks to shallow water sediments that document the formation and evolution of oceanic lithosphere. Radiometric dating of these ophiolitic rocks constrains the timing of different phases of Tethyan expansion, while their geochemical compositions reveal information about mantle sources and the thermal evolution of spreading centers. Strange that an ocean basin should serve simultaneously as a barrier and a connection. isolating continental biotas while linking marine provinces that had previously been separated by continental landmasses. The tethys creates new patterns of biological provincialism as terrestrial organisms on different continents evolve in isolation, while marine organisms experience enhanced opportunities for dispersal and genetic exchange across the expanding oceanic realm. These contrasting effects on terrestrial and marine biogeography create complex patterns of biodiversity that influence evolutionary trajectories for millions of years. Carbonate platform development along Tethyan margins creates some of the most extensive shallow marine environments in Earth's history. With reef systems and carbonate banks extending for thousands of kilometers along continental edges, these platforms support highly diverse marine communities that include not only reef-building organisms but also complex assemblages of echinoids, mollusks, foraminifera, and other groups that exploit the three-dimensional habitat structure created by carbonate construction. The carbonate platforms also serve as massive carbon sinks, extracting carbon dioxide from seawater and atmosphere through biological and chemical precipitation processes that influence global carbon cycling. Deep water formation in the tethys develops as the ocean basin matures and establishes thermal gradients sufficient to drive thermohaline circulation. The formation of deep water masses requires specific combinations of temperature, salinity, and density that develop as the ocean basin widens and deepens beyond critical threshold values. These deep water masses carry dissolved oxygen to abyssal depths, supporting deep-sea ecosystems and preventing the development of the anoxic conditions that characterize restricted marine basins. The establishment of deep-water circulation marks a critical transition in the evolution of the tethys from a restricted seaway to a fully oceanic system. Hydrothermal activity along Tethyan spreading centers creates distinctive mineral deposits and supports chemosynthetic ecosystems that thrive in the chemical energy provided by volcanic processes. These hydrothermal systems generate massive sulfide deposits that concentrate copper, zinc, lead, and precious metals in economically important ore bodies. The hydrothermal ecosystems themselves support unique communities of bacteria, tube worms, and other organisms that derive energy from chemical reactions rather than photosynthesis, creating biological communities that can survive in the absence of sunlight and serve as analogs for possible life in extraterrestrial environments. Sedimentary sequences deposited in the tethys preserve detailed records of environmental change, biological evolution, and oceanographic conditions spanning hundreds of millions of years. These sequences include distinctive phase-size associations that reflect different depositional environments, from shallow carbonate platforms to deep marine turbidite systems. The sedimentary record documents major environmental transitions, including sea level fluctuations, climate changes, and biological extinction and radiation events that affected Tethyan ecosystems. Stable isotope compositions of marine fossils from these sequences provide quantitative information about ancient ocean temperatures, ice volumes, and biogeochemical cycling. Volcanic island arcs develop within the tethys as oceanic crust subducts beneath continental margins and creates magmatic systems that build chains of volcanic islands. These island arcs serve as stepping stones for biological dispersal between continental areas, allowing some terrestrial organisms to maintain genetic connectivity across the expanding ocean basin. The volcanic islands also create new terrestrial habitats in oceanic settings, supporting endemic biotas that evolve in isolation from continental influences. The geological evolution of these island arcs preserves evidence of subduction processes, magma generation, and the complex interactions between oceanic and continental crustal systems. Climate effects of tethyon expansion include the development of more pronounced seasonal contrasts and the strengthening of monsoon systems as the ocean basin creates new sources of atmospheric moisture and alters the distribution of heat between oceanic and continental regions. The east-west orientation of the tethys allows tropical circulation systems to develop across much of the low-latitude region, transporting heat and moisture between different continental areas and oceanic basins. These circulation changes influence precipitation patterns, temperature regimes, and the distribution of vegetation zones across adjacent continental areas. Biological innovation within Tethyan ecosystems includes the evolution of new feeding strategies, reproductive mechanisms, and morphological adaptations that allow organisms to exploit the environmental opportunities created by oceanic expansion. Planktonic organisms develop increasingly sophisticated shell structures and life cycle strategies that enhance their competitive abilities in open oceanic environments. Benthic communities evolve complex ecological relationships involving symbiosis, predation, and chemical defense that increase ecosystem stability and productivity. These evolutionary innovations contribute to the diversification of marine life and the establishment of ecological patterns that persist throughout subsequent geological periods. Geochemical evolution of Tethyan seawater reflects the complex interactions between volcanic inputs, biological processes, and exchange with other ocean basins through developing circulation systems. Trace element concentrations and isotopic compositions of Tethyan sediments provide evidence of changing weathering patterns, volcanic activity, and biological productivity as the ocean basin evolves from a restricted seaway to a mature oceanic system. These geochemical signatures allow reconstruction of ancient environmental conditions and provide quantitative constraints on models of ocean atmosphere evolution during continental breakup. Only took 50 million years for the Tethys to evolve from a narrow seaway into a major ocean basin that influenced global climate and biological evolution. The Tethyan expansion represents one of the most significant paleoceanographic events in Earth's history, creating circulation patterns and environmental conditions that shaped the evolution of life throughout the Mesozoic era. The legacy of the Tethys can still be seen in the distribution of marine fossils, the structural geology of mountain belts formed by subsequent continental collision, and the geochemical signatures preserved in sedimentary sequences that document this remarkable phase of Earth's oceanographic evolution. Gondwana's southern breakup unfolds as Antarctica. Australia and India begin their slow drift away from Africa, fragmenting the southern portion of the ancient supercontinent through processes that operate with the inexorable patience of deep geological time. This fragmentation represents one of the most complex episodes of continental breakup in Earth's history, involving the simultaneous separation of multiple continental fragments along rift systems that intersect at triple junctions and propagate according to the geometric constraints imposed by spherical geometry and mantle convection patterns. The breakup process requires tens of millions of years to complete, with different phases of rifting and seafloor spreading, creating a complex pattern of oceanic basins and continental margins around the southern polar region. The initiation of southern Gondwana breakup appears to be related to mantle plume activity beneath the supercontinent, with thermal anomalies creating uplift, volcanism, and mechanical weakening that facilitate the onset of continental rifting. Large igneous provinces develop where mantle plumes intersect the continental lithosphere, creating massive outpourings of flood basalts that cover vast areas with volcanic rocks and release enormous quantities of gases into the atmosphere. These volcanic events have significant effects on global climate and may trigger environmental changes that influence biological evolution throughout the southern hemisphere. The relationship between mantle plumes and continental breakup remains an active area of research, with debates continuing about the relative importance of active versus passive rifting mechanisms. Scientists reconstruct the geometry and timing of Gondwana breakup through integration of magnetic anomaly patterns, radiometric ages of volcanic rocks, and the structural relationships preserved in continental margins around the southern ocean basins. The magnetic anomaly patterns provide detailed information about spreading rates, ridge reorganizations, and the relative motions of different continental fragments as they separated from the main body of Gondwana. Hotspot tracks preserved on the separated continents allow reconstruction of absolute plate motions and provide constraints on the deep mantle processes that drove the breakup. The precision of these reconstructions continues to improve as new data become available and analytical techniques advance. Strange that continental fragmentation should create both isolation and connection simultaneously, separating terrestrial biotas while creating new oceanic pathways that enhance marine biological exchange. The opening of the Southern Ocean fundamentally alters global ocean circulation by establishing the Antarctic Circumpolar Current, a massive oceanic circulation system that isolates Antarctica from warmer waters and contributes to the development of permanent ice sheets on the Antarctic continent. This circulation change has profound effects on global climate, creating the thermal isolation necessary for Antarctic glaciation while influencing temperature and precipitation patterns throughout the southern hemisphere. Marine ecosystems in the newly formed southern ocean basins develop characteristics that reflect the unique environmental conditions created by continental fragmentation in polar and subpolar regions. Cold-water marine communities evolve adaptations to low temperatures, seasonal ice cover, and the distinctive oceanographic conditions that characterize high-latitude marine environments. These ecosystems support high levels of primary productivity during summer months, when sea ice retreats and sunlight becomes available for photosynthesis, while maintaining reduced activity during winter months when ice cover and darkness limit biological processes. The seasonal extremes characteristic of polar marine environments create selective pressures that drive the evolution of specialized physiological and behavioral adaptations. Sedimentary sequences deposited during Gondwana breakup preserve detailed records of environmental change and volcanic activity associated with continental fragmentation. These sequences include distinctive facies associations that reflect the transition from continental to marine depositional environments, with rift basin sediments overlain by marine sequences that document the gradual flooding of continental margins as ocean basins widen and deepen. Glacial deposits within these sequences provide evidence of ice sheet development on the separating continents, while volcanic ash layers create precise time markers that allow correlation of events across different oceanic basins. Biological consequences of Gondwana breakup include the isolation of terrestrial biotas on different continents and the creation of new opportunities for allopatric speciation and adaptive radiation. The separation of Australia from Antarctica eliminates land connections that had allowed biological exchange between these continents, leading to independent evolutionary trajectories that create the distinctive biotas that characterize these regions today. The isolation of Madagascar from Africa similarly creates opportunities for endemic evolution on this large island, while the northward drift of India creates complex biogeographic patterns as this continent carries its biota toward eventual collision with Asia. Paleoclimate modeling suggests that Gondwana breakup has significant effects on atmospheric and oceanic circulation patterns, with the creation of new oceanic basins altering the distribution of heat and moisture between different regions. The development of the Antarctic Circumpolar Current creates thermal isolation around Antarctica that contributes to global cooling and may influence the long-term evolution of climate toward the icehouse conditions that characterize much of the Cenozoic era. These climate changes have cascading effects on terrestrial and marine ecosystems, influencing vegetation patterns, ecosystem productivity, and the geographical distribution of different biological communities. Volcanic activity associated with Gondwana breakup creates distinctive rock formations that preserve evidence of the rifting and spreading processes involved in continental fragmentation. Flood basalt provinces mark the locations where mantle plumes intersected the continental lithosphere, while oceanic basalts formed at spreading centers document the progressive development of oceanic crust between the separating continents. The geochemical compositions of these volcanic rocks provide information about mantle sources, melting processes, and the thermal evolution of the rifting system. Some of these volcanic provinces rank among the largest igneous events in Earth's history, with volumes of erupted material sufficient to influence global environmental conditions. Deep crustal structure beneath the southern ocean basins reveals evidence of the complex extensional processes that operated during continental breakup. Seismic reflection profiles show thick sequences of rift-related sediments overlying highly extended continental crust, with some margins exhibiting extreme thinning that approaches the transition to oceanic crust formation. These structural relationships provide insights into the mechanisms of continental breakup and the processes that control the geometry and evolution of passive continental margins. The preservation of continental crust fragments within oceanic basins creates complex patterns of crustal heterogeneity that influence subsequent geological processes. Hydrothermal circulation through young oceanic crust created during Gondwana breakup generates distinctive mineral deposits and influences ocean chemistry through the exchange of heat and dissolved constituents between seawater and volcanic rocks. These hydrothermal systems create massive sulfide deposits that concentrate base and precious metals in economically important ore bodies, while also supporting chemosynthetic ecosystems that derive energy from chemical reactions rather than photosynthesis. The hydrothermal flux from these systems influences global ocean chemistry and may contribute to long-term changes in seawater composition and marine ecosystem productivity. Continental margin evolution around the southern ocean basins follows predictable patterns of thermal subsidence and sediment accumulation that create some of the thickest sedimentary sequences in the geological record. These margin sequences preserve continuous records of environmental change spanning hundreds of millions of years, with climate proxy data that document the long-term evolution of southern hemisphere environmental conditions. The sedimentary record from these margins provides critical constraints on models of ice sheet development, sea level change, and the evolution of ocean circulation patterns during the transition from greenhouse to icehouse climates. Only took 100 million years for Gondwana breakup to completely reorganize the geography of the southern hemisphere and create the oceanic circulation patterns that persist to the present day. The fragmentation of this ancient supercontinent represents one of the most significant geographical changes in Earth's recent history, influencing biological evolution, climate development, and the distribution of natural resources throughout the southern continents. The legacy of Gondwana breakup can still be seen in the distinctive biogeographic patterns that characterize the southern continents, the structural geology of passive margins around the southern ocean basins, and the unique environmental conditions that make Antarctica the coldest and most isolated continent on Earth. Modern continents take shape as the familiar outlines of today's landmasses emerge from the complex processes of rifting, spreading, and collision that have redistributed continental fragments across the planet's surface since the breakup of Pangaea began more than 200 million years ago. The continental configurations that characterize the present-day world represent a temporary arrangement in the ongoing cycle of supercontinent assembly and dispersal, with each continent carrying within its geological structure the history of ancient collisions, rifting events, and the gradual accumulation of crustal material through billions of years of plate tectonic processes. These familiar shapes that appear so permanent from a human perspective continue to change at rates of centimeters per year, following trajectories determined by mantle convection patterns and the gravitational forces that drive continental drift. North America assumes its recognizable configuration through a complex history of continental growth, rifting, and collision that spans the entire geological record. The continent's eastern margin preserves evidence of the collision events that assembled Pangaea, while its western margin shows the effects of ongoing subduction and terrain accretion that continue to add new crustal material to the continental edge. The opening of the Atlantic Ocean creates the passive eastern margin that will persist for hundreds of millions of years, while the Pacific margin remains tectonically active as oceanic plates continue to subduct beneath the continental edge. This contrast between passive and active margins reflects the fundamental asymmetry of plate tectonic processes and creates the distinctive geological and topographic characteristics that define different parts of the continent. South America develops its elongated north-south configuration through separation from Africa and subsequent collision with oceanic and continental terrains along its western margin. The continent's eastern margin preserves one of the world's best examples of a passive continental margin, with thick sedimentary sequences that document the gradual subsidence and sediment accumulation that characterize rifted continental edges. The Andes Mountains along the western margin represent one of the longest and most continuous mountain chains on Earth, formed by ongoing subduction of oceanic crust beneath the South American plate. This subduction system generates the volcanic activity, crustal deformation, and mineral deposits that make the Andes one of the most geologically active regions on the planet. Scientists trace the evolution of continental configurations through careful analysis of magnetic anomaly patterns, hotspot tracks, and the distribution of geological provinces that preserve evidence of ancient tectonic processes. Plate reconstruction models allow precise determination of continental positions at different times in the past, revealing the complex pathways followed by continental fragments as they separated from Pangaea and drifted toward their present positions. These reconstructions show that continental motion has not been uniform or linear, with periods of rapid drift alternating with intervals of slower movement as plate boundaries reorganize and new tectonic forces develop. Strange that continents should appear so stable and permanent when viewed from human timescales, yet maintain such mobility over geological time that their positions have changed by thousands of kilometers since the breakup of Pangaea. The apparent permanence of continental positions reflects the enormous scale of geological processes and the vast timescales over which they operate, creating an illusion of stability that masks the continuous motion and deformation that characterize the Earth's surface. The scale discrepancy between human perception and geological reality illustrates the fundamental challenge of understanding processes that operate over timescales far beyond direct human experience. Africa maintains its position near the center of Pangaea's former configuration, while other continents drift away, creating the distinctive pattern of oceanic basins that surround the African continent. The Red Sea and Gulf of Aden preserve active examples of continental rifting, showing the processes that separated other continents from Africa in the geological past. The East African Rift System represents the initial stages of continental breakup that may eventually separate Eastern Africa from the main part of the continent, creating a new oceanic basin and continuing the cycle of continental fragmentation. These active rifting processes provide natural laboratories for studying the mechanisms of continental breakup and testing models of how supercontinents fragment and disperse. Europe develops its complex configuration through collision with Africa and the closure of the Tethys Ocean, creating the alpine Himalayan mountain belt that extends across southern Europe and into Asia. This collision zone represents one of the most active tectonic regions on Earth, with ongoing convergence between African and European plates generating earthquakes, volcanic activity, and continued mountain building. The Mediterranean Sea represents a remnant of the once vast Tethys Ocean, preserving evidence of the complex processes involved in oceanic closure and continental collision. The geological structure of Europe reflects its assembly from multiple smaller continental fragments and oceanic terrains that were accreted during various collision events. Asia achieves its enormous size through the collision and amalgamation of numerous continental fragments that originated in different parts of the ancient ocean system. The collision of India with Asia creates the Himalayan mountain belt and the Tibetan Plateau, the highest and most extensive high-elevation region on Earth. This collision continues today, with India penetrating several thousand kilometers into the Asian continent and generating the tectonic forces that create earthquakes throughout Central and Eastern Asia. The suturing of different continental blocks within Asia creates a complex mosaic of geological terrains that preserve evidence of ancient ocean basins, volcanic arcs, and collision zones. Australia's northward drift carries the continent from polar positions in Gondwana toward its present location in tropical and subtropical latitudes, creating dramatic changes in climate and biological evolution. The continent's isolation following separation from Antarctica allows the evolution of distinctive biotas that include many endemic groups found nowhere else on Earth. The continental structure of Australia preserves some of the oldest rocks on Earth in its Precambrian shield regions, while younger rocks around the continental margins document the various rifting and collision events that shaped the continent's evolution. The continent's mineral wealth reflects this complex geological history, with ore deposits formed during different tectonic episodes, providing economically important resources. India's remarkable journey from Gondwana to collision with Asia represents one of the fastest episodes of continental drift in the geological record, with the subcontinent traveling more than 6,000 kilometers across the ancient Tethys Ocean. This rapid motion reflects the unique configuration of spreading centers and subduction zones that drove Indian plate motion, creating oceanic crustal production rates that exceeded those of most other plate tectonic systems. The collision of India with Asia generates not only the Himalayan mountain belt, but also extensive intracontinental deformation that affects regions thousands of kilometers from the collision zone itself. Antarctica's position over the South Pole creates the unique environmental conditions that support the development of continental ice sheets and establish the polar climate system that influences global ocean circulation and atmospheric patterns. The continent's isolation by the Antarctic circumpolar current creates thermal conditions that allow ice sheets to persist even during periods of elevated global temperatures, making Antarctica a critical component of the global climate system. The geological structure beneath the ice preserves evidence of Antarctica's former connections to other Gondwana continents, including coal deposits and fossil forests that document warmer climates when the continent occupied lower latitudes. Oceanic circulation patterns around the modern continental configuration create the complex current systems that transport heat, nutrients, and dissolved gases between different ocean basins. The Atlantic Ocean develops its characteristic meridional overturning circulation as the basin widens and matures, while the Pacific Ocean maintains its vast size and distinctive circulation patterns that influence climate throughout the Pacific Rim region. The Indian Ocean emerges as a separate oceanic basin following the breakup of Gondwana, developing its own circulation systems and seasonal patterns that reflect the unique configuration of surrounding continental masses. Biological evolution on the separated continents follows independent pathways that create the distinctive biogeographic patterns that characterize the modern world. Continental isolation allows allopatric speciation and adaptive radiation to proceed without genetic exchange between populations, leading to the development of endemic biotas that reflect both the environmental conditions and the evolutionary history of each continent. Some groups achieve cosmopolitan distributions through dispersal across oceanic barriers, while others remain restricted to single continents or biogeographic regions, creating complex patterns of similarity and difference between continental biotas. Climate evolution during the transition to modern continental configurations reflects the complex interactions between changing geography, ocean circulation, and atmospheric composition. The gradual closure of tropical seaways and the opening of high-latitude oceanic passages create the circulation patterns that contribute to global cooling and the eventual development of polar ice sheets. These climate changes influence biological evolution, ecosystem development, and the distribution of sedimentary environments that preserve records of environmental change throughout the Cenozoic era. Sedimentary sequences deposited during the evolution toward modern continental configurations preserve detailed records of sea level change, climate variation, and biological evolution spanning the past 200 million years. These sequences document the environmental consequences of continental breakup, ocean basin formation, and the gradual reorganization of global circulation systems. The sedimentary record from continental margins provides particularly complete archives of environmental change, with continuous sequences that allow precise correlation of geological and biological events across different regions and time intervals. Mineral resource distribution reflects the complex geological history of continental assembly, breakup, and subsequent evolution, with different types of ore deposits associated with specific tectonic environments and geological processes. The breakup of Pangaea redistributed existing mineral resources among different continents while creating new opportunities for ore formation through rifting, volcanism, and subsequent geological processes. Understanding the geological controls on mineral resource distribution requires detailed knowledge of continental evolution and the tectonic processes that concentrate economically important elements in accessible deposits. Geodynamic modeling of continental motion shows that the present configuration of continents represents only a temporary arrangement in the ongoing cycle of supercontinent assembly and dispersal. Mantle convection patterns that currently drive continental drift will continue to operate, gradually moving the continents toward new configurations that may eventually lead to the assembly of a new supercontinent in the distant future. These modeling studies suggest that the Atlantic Ocean will eventually stop expanding and begin to contract, while new oceanic basins may form through rifting of existing continents. Only took 200 million years for continental breakup to transform the single landmass of Pangaea into the familiar continental configuration that characterizes the modern world. This transformation represents one of the most dramatic geographical changes in Earth's recent history, influencing virtually every aspect of the planet's environmental and biological systems. The modern continental configuration provides the geographical framework for current climate patterns, ocean circulation systems, and biogeographic distributions that define the environmental conditions under which contemporary life has evolved. Paleomagnetic data from the separated continents provide precise constraints on the timing and geometry of continental drift, allowing reconstruction of plate motions with unprecedented accuracy. These data show that continental drift rates have varied significantly through time, with periods of rapid motion alternating with intervals of slower drift, as plate boundary configurations change and new tectonic forces develop. The paleomagnetic record also documents changes in the Earth's magnetic field that may be related to deep mantle processes and core dynamics that drive both continental drift and magnetic field generation. The legacy of Pangaea breakup can still be seen in the geological structure, biological distributions, and resource endowments of the modern continents, providing evidence of their shared history as parts of a single ancient landmass. Mountain belts, sedimentary basin, and igneous provinces that formed during the assembly and breakup of Pangaea continue to influence landscape evolution, natural hazard patterns, and economic geology throughout the modern world. Understanding this geological heritage provides critical insights into the processes that shape continental evolution and the long-term dynamics of the Earth system. Future continental evolution will be driven by the same plate tectonic processes that created the present continental configuration. But the specific outcomes remain difficult to predict due to the complex interactions between mantle convection, lithospheric structure, and surface processes. Current patterns of seismic activity, volcanic eruptions, and crustal deformation provide clues about ongoing tectonic processes, while geodynamic models attempt to project these processes forward to predict future continental configurations. These predictions suggest that continental drift will continue for billions of years, eventually creating new supercontinents and oceanic basins as the cycle of continental assembly and dispersal continues its endless progression through geological time. Deep time's patient cycles continue as the scattered continents follow their eternal drift toward the next supercontinent assembly, moving according to mantle convection patterns that operate with the same fundamental physics that dispersed Pangaea and will eventually gather Earth's landmasses into new configurations billions of years hence. The present arrangement of continents represents merely one frame in the endless motion picture of continental drift, a temporary configuration that appears permanent only from the limited perspective of human timescales, but remains as transient as any other moment in the 4.5 billion year history of plate tectonics. These vast cycles of assembly and dispersal operate according to the thermodynamics of planetary heat loss, the mechanics of lithospheric deformation, and the gravitational forces that drive mantle convection with a patience that spans hundreds of millions of years per complete cycle. Computer models of future plate motion suggest us that the Atlantic Ocean will eventually stop expanding and begin to contract as new subduction zones develop along its margins, reversing the process that opened this oceanic basin more than 200 million years ago. The Pacific Ocean appears destined to close as the continents surrounding its margins continue to converge, eliminating the largest oceanic basin on the modern Earth and bringing together landmasses that have been separated for hundreds of millions of years. These predictions remain uncertain due to the complex feedback relationships between mantle convection, lithospheric structure, and surface processes, but they illustrate the fundamental tendency of plate tectonic systems to reorganize continuously over geological time. The physics of supercontinent cycles reflects the balance between the forces that drive continental assembly and those that promote continental dispersal, with thermal insulation effects playing a critical role in determining the timing and location of future breakup events. When continents cluster together into supercontinents, they create thermal boundary layers that restrict heat loss from the underlying mantle, generating thermal anomalies that eventually lead to rifting and dispersal. The dispersed phase of the cycle allows more efficient heat loss through oceanic lithosphere, gradually cooling the mantle until thermal contraction and gravitational forces begin to drive the continents back together into the next supercontinent assembly. Scientists estimate that complete supercontinent cycles require approximately 4 to 600 million years, with the dispersed phase typically lasting longer than the assembly phase due to the geometric constraints of continental collision and the time required for oceanic basins to close through subduction processes. The Pangaea cycle represents the most recent complete example of this process, with assembly occurring during the late Paleozoic and early Mesozoic, followed by dispersal that continues to the present day. The next supercontinent, sometimes called Pangaea Proxima or Amasia depending on the specific configuration predicted by different models, may begin to assemble within the next few hundred million years as current patterns of continental drift bring the scattered landmasses back together. Strange that geological processes operating over such vast timescales should follow predictable patterns and exhibit cyclic behavior. Yet the fundamental physics of heat transfer, gravitational attraction, and thermodynamic equilibrium create systematic tendencies that persist throughout Earth's history. The supercontinent cycle represents one of the most fundamental rhythms of Earth's geological evolution, influencing climate patterns, biological evolution, and the distribution of natural resources over timescales that span significant portions of the planet's history. These cycles operate independently of biological processes, driven by physical forces that would continue even in the absence of life. Yet, they create the environmental variations that provide opportunities and challenges for evolutionary innovation. Biological evolution responds to supercontinent cycles through patterns of speciation, extinction, and biogeographic reorganization that reflect the changing connectivity and environmental conditions associated with continental assembly and dispersal. The assembly phase typically promotes biological exchange and competitive interactions that may trigger extinction events, while the dispersal phase creates opportunities for allopatric speciation and adaptive radiation as populations become isolated on different continents. These biological responses to supercontinent cycles contribute to the long-term patterns of biodiversity change that characterize Earth's evolutionary history. Climate effects of supercontinent cycles include systematic variations in global temperature, atmospheric composition, and precipitation patterns that reflect the influence of continental configuration on ocean circulation, atmospheric dynamics, and biogeochemical cycling. Supercontinent assembly tends to create more extreme continental climates with reduced oceanic moderation, while dispersal phases typically promote more equable climate conditions with enhanced oceanic heat transport. These climate variations influence biological evolution, ecosystem development, and the formation of sedimentary deposits that preserve records of environmental change throughout geological time. Ocean chemistry cycles reflect the changing balance between continental weathering, oceanic crust production, and biological productivity that accompanies supercontinent assembly and dispersal. The dispersal phase typically enhances seafloor spreading and hydrothermal activity that influences ocean chemistry through increased inputs of dissolved minerals and trace elements. Continental assembly may alter weathering patterns and river chemistry, changing the flux of nutrients and dissolved constituents to marine environments. These ocean chemistry variations influence marine ecosystems and the precipitation of chemical sediments that preserve records of ancient oceanic conditions. Mantle dynamics drive supercontinent cycles through convection patterns that change in response to the thermal boundary conditions imposed by different continental configurations. Numerical models of mantle convection suggest that supercontinents create long-wavelength thermal anomalies that persist for hundreds of millions of years, influencing the location and intensity of mantle upwelling and downwelling that drive plate tectonics. The feedback relationships between surface tectonics and deep mantle processes remain subjects of active research, with ongoing debates about the relative importance of top-down versus bottom-up forcing in controlling supercontinent cycles. Mineral resource formation shows systematic relationships to supercontinent cycles, with different types of ore deposits associated with specific phases of continental assembly and dispersal. The assembly phase typically generates collision-related deposits including porphyry copper systems, orogenic gold deposits, and various types of metamorphic and magmatic ore bodies. The dispersal phase creates rift-related deposits, including sedimentary copper deposits, evaporite formations, and the massive sulfide deposits associated with seafloor spreading. Understanding these relationships helps predict the distribution of undiscovered mineral resources and guides exploration strategies for economically important commodities. Atmospheric evolution over supercontinent cycles reflects the complex interactions between volcanic outgassing, biological productivity, and chemical weathering that control atmospheric composition over geological timescales. Major volcanic events associated with continental breakup can release enormous quantities of greenhouse gases that influence global climate for millions of years. While enhanced weathering during periods of continental dispersal may remove carbon dioxide from the atmosphere and contribute to global cooling, these atmospheric variations create feedback loops that influence both climate evolution and biological productivity throughout supercontinent cycles. The inevitability of future supercontinent assembly reflects the fundamental tendency of thermodynamic systems to minimize energy through the reduction of surface area and the optimization of heat transfer processes. Continental clustering reduces the total length of continental margins and oceanic spreading centers, creating more efficient configurations for planetary heat loss. However, the specific geometry and timing of future supercontinent assembly remain uncertain due to the complex interactions between multiple forcing mechanisms and the sensitivity of the Earth system to small perturbations in initial conditions. Only took 4.5 billion years for Earth to develop the plate tectonic system that drives supercontinent cycles. Yet these cycles will continue for billions of years into the future as long as the planet retains sufficient internal heat to drive mantle convection. The longevity of plate tectonic processes depends on the gradual cooling of the Earth's interior and the efficiency of heat transfer mechanisms, with current models suggesting that plate tectonics may persist for another billion to 2 billion years before the planet's internal heat budget declines below the threshold necessary to maintain lithospheric mobility. Deep time perspectives on supercontinent cycles reveal the fundamental unity underlying Earth's apparent complexity. With seemingly chaotic geological processes following predictable patterns when viewed over appropriate temporal and spatial scales, the cyclical nature of continental assembly and dispersal creates a temporal framework for understanding Earth's evolution that transcends the specific details of individual geological events and provides insights into the long-term behavior of planetary systems. These cycles connect the deep past with the distant future, illustrating the continuity of geological processes that operate with patience and persistence across the vast expanse of geological time. The completion of current supercontinent cycles will create new continental configurations that may support different climate systems, biological communities, and geological processes than those that characterize the present Earth. However, the fundamental patterns of assembly and dispersal will continue, driven by the same physical forces that have shaped continental evolution throughout Earth's history. Future geologists studying these ancient processes from the perspective of the next supercontinent will see the current continental configuration as merely another temporary arrangement in the endless dance of continents across the planet's surface. A brief moment in the eternal cycles that connect Earth's geological past with its unimaginably distant future. The continents rest now in their temporary positions, scattered across the blue planet like ancient puzzle pieces waiting for time's next patient rearrangement. Antarctica sleeps beneath its ice. Australia drifts slowly northward through tropical seas. And the Atlantic continues its imperceptible widening while the Pacific gradually narrows. Each landmass carries within its rocks the memory of Pangaea, the scars of ancient collisions, and the quiet promise of future gatherings yet to come. Somewhere beneath the mantle's slow circulation, thermal currents rise and fall according to laws older than life itself, following patterns that will outlast mountains and outlive continents. The Earth turns through space with its cargo of stone and water, ice and fire, carrying forward the stories written in granite and limestone, in the magnetic signatures of basalt and the patient accumulation of sediment on ocean floors that will never know sunlight. Time flows onward with geological patience, measuring change in millimeters per year in the gradual drift of magnetic poles, in the slow metamorphosis of rock into different rock through pressures that require millions of years to complete their work. The supercontinent cycle continues its ancient rhythm, neither hurried nor delayed by the brief emergence of consciousness that has learned to read the messages hidden in stone. In this moment between assembly and the next assembly, between one configuration of continents and another, the planet rests in the particular arrangement of land and sea that has shaped all human understanding of geography. Yet this arrangement too shall pass, yielding to the deeper patterns that govern planetary evolution, to forces that operate beyond the scale of human time and continue their work in silence, in darkness, in the patient depths where stone learns to flow and continents learn to dance across the surface of a world that measures eternity in the movement of its own substance through space and time. Sleep well in this knowledge of deep time, in the understanding that change and permanence are simply matters of scale, that the solid earth beneath us moves with the same fluid grace that carries clouds across the sky, but across timescales so vast that mountains rise and fall like slow breathing, and continents drift apart and come together like thoughts in the mind of a dreaming planet.